Buenos días, ya estamos al vivo en el TensorFlow Everywhere el TensorFlow User Group de Bolivia, Latinoamérica. Quiero presentarle a Leigh Zerna. Ella es la líder del TensorFlow Group de Bolivia y también es Google Developer Expert en Machine Learning. Muy buenos días, Leigh. Gracias por participar, por organizar toda esta reunión bastante importante sobre TensorFlow para nuestra comunidad, para nuestro grupo de personas. Espero que el programa que hemos preparado con los excelentes expositores que has invitado realmente sea de mucho provecho para todas las personas que nos están viendo y que podamos de esta manera mejorar el nivel de nuestro TensorFlow en nuestro país y en nuestra región. Muchísimas gracias, Leigh. Te cedo la palabra.
Muchas gracias, Fernando, y gracias también por el apoyo en este evento, principalmente. Y pues muy buenos días para todos. Muchísimas gracias por darse este tiempo. A las personas que han podido reservar por Meetup, donde estamos como TensorFlow User Group Bolivia, y también para las personas que ahora nos acompañan por YouTube. Estamos otra vez muy contentos de poder ser parte de este evento global que se ha trabajado desde diferentes países del mundo, desde diferentes, ¿cómo se llama?, grupos de TensorFlow User Group, que están justamente promoviendo todos los temas de Machine Learning, inteligencia artificial, y pues cómo motivar a más personas a trabajar con todo esto. Rápidamente me presento, después de la presentación de Fernando, muchísimas gracias. Desde el año pasado vamos trabajando con lo que es este TensorFlow User Group. Básicamente es un equipo de trabajo en el cual hacemos diferentes meetups, en el cual también se pueden desarrollar diferentes actividades, como leer papers y demás. Y pues para nosotros es muy importante compartir todo este conocimiento con lo que es la comunidad, ¿no? Que queremos también traer diferentes personas que están todo el tiempo relacionadas a inteligencia artificial, a TensorFlow como herramienta, y es justamente que en este evento tenemos personas de diferentes partes del mundo también que nos acompañan y que van a estar compartiendo sus proyectos y sus experiencias en todo esto. Así que vamos contándoles un poco más sobre la agenda que tenemos preparada para el día de hoy. Súper. Vamos a contarles, perdón, la agenda que les tenemos preparada para el día de hoy. Y enseguida ya estamos. Así que también se pueden compartir sobre este evento en sus redes sociales. Está, por ejemplo, acá los hashtags TensorFlow, TF Everywhere, y pues toda esta información para que podamos hacer crecer esta comunidad más grande. Entonces, ya que comenzamos, Fernando, si podemos ir a la siguiente pantalla, por favor. Súper. Sí, justamente, otra vez, mi nombre es Leigh, y contarles un poco sobre lo que son los primeros pasos en TensorFlow en general, principalmente enfocado en todo lo que es la parte de la documentación y las novedades, pero enseguida les vamos a contar también sobre los speakers que vamos a tener ahora. El siguiente, por favor. Desde Nueva York, desde Google Nueva York, tenemos a Josh Gordon. Él nos va a estar hablando sobre introducción al Deep Learning. Esta charla es en inglés, pero vamos a mostrar los subtítulos ahí. Contarles un poco sobre Josh. Él trabaja en el equipo de TensorFlow en Google y enseña mucho sobre todo lo que es el Deep Learning aplicado en la Universidad de Columbia. Y también enseña Machine Learning en Pace University. Y pues él se encuentra en Twitter como Random Forest. Igual si pueden seguirlo y ver un poco más de su información. En minutos él nos va a estar acompañando con esta charla que es Intro a Deep Learning. Siguiente, por favor. También tenemos desde Brasil a Bianca, Bianca Ximenes. Su charla es Machine Learning en producción y cómo ese es el reto para millones, ¿verdad? Entonces ya hablar un poco más de lo básico al tema de lo que viene a ser producción, contarles un poco de Bianca, pues ella es Product Manager de Inteligencia Artificial en Guppy y es responsable de diferentes actividades dentro de la empresa, además que ayuda en temas de reclutamiento. Y pues ella también es Google Developer Expert en Machine Learning, es candidata a un doctorado en Ciencias de Computación allá en Brasil, y pues su trabajo está bastante enfocado en todo lo que es los temas de Machine Learning, principalmente en lo que vienen a ser los productos centrados en el humano, potencializados por inteligencia artificial, así también temas de ética, sobre Machine Learning en la sociedad, y pues ella aplica bastante todo lo que es la temática de los productos enfocados en todo lo que vienen a ser datos. Así que también las personas que nos siguen pueden hacer sus preguntas por acá cuando tengamos a Bianca con el tema de lo que es Machine Learning en producción. Siguiente, por favor. En la siguiente charla, desde Bolivia, tenemos a nuestro amigo José Laruta. Él nos va a presentar Desplegando tu modelo de TensorFlow como un servicio en la nube. Contarles que José, pues, es uno de los pocos certificados de TensorFlow a nivel Latinoamérica. José es ingeniero electrónico, también se desempeña como desarrollador de software en full stack. Tiene esa experiencia, ¿no?, en software empresarial, sistemas distribuidos, sistemas embebidos, robots interactivos. Hizo su certificación como Developer Certificate TensorFlow. Es profesor en la universidad con temáticas de inteligencia artificial y machine learning. Y pues nos va a estar contando, como les decía, desplegando tu modelo de TensorFlow como un servicio en la nube. El siguiente, por favor. Y desde San Francisco también tenemos otra invitada especial, que es Leigh Johnson. Ella nos va a hablar un poco de lo que es Machine Learning Ops, la parte operativa en el extremo, on edge. Y pues nos cuenta el tema de cómo hacer las operaciones, ¿no?, con Machine Learning y trabajarlo desde su propio data center o desde una nube virtual privada, además de cómo llevar y extender todo esto a lo que vienen a ser los dispositivos de IoT, que son también especiales, ¿no?, embebidos para poder hacer todo este tema de lo que viene a ser inteligencia, específicamente Machine Learning. Nos va a mostrar un poco de cómo ella también trabaja en temas de detección, en temas de monitoreo, con sistemas de impresoras en 3D. Así que imperdible también esta charla, contarles que Leigh, ella es Machine Learning Engineer, ingeniera en Machine Learning en Slack, en San Francisco, y también es Google Developer Expert en temas de Machine Learning. Entonces, les invitamos también a acompañarnos en la charla de Leigh. Y siguiente, por favor. Y para concluir este TensorFlow Everywhere, tenemos a Joanna Carrasqueira, que ella es la encargada de lo que son relaciones de desarrolladores como Program Manager, específicamente para la comunidad de lo que es TensorFlow en Google. También desde San Francisco nos va a estar contando un poco más sobre la comunidad y sobre las estrategias globales que ellos tienen. Entonces también nuestra invitada especial para contarnos un poco más de, como decía, toda la comunidad de lo que es TensorFlow. Y pues antes de pasar a la charla con nuestro primer invitado y contándoles un poco sobre lo que es la parte de TensorFlow y otra vez darles la bienvenida, quiero contarles sobre TensorFlow, lo que vendrían a ser los primeros pasos. Sin ninguna diapositiva especial, contarles un poco sobre la documentación y sobre la herramienta en sí misma. Si ustedes son nuevos y no han escuchado antes, pues TensorFlow es una herramienta de Google que en realidad permite trabajar con modelos de lo que son redes neuronales artificiales, algo muy importante dentro de todo lo que es inteligencia artificial, y pues que en los últimos años ha evolucionado bastante desde ser una herramienta para trabajarla solo con C++, con Python, a ser una herramienta en la cual pues se extiende no solamente a lo que ya conocíamos como para hacer proyectos y luego deployarlos en servidores, sino también a trabajarlo, por ejemplo, con JavaScript para aquellas personas que tienen más conocimiento en esta tecnología. También está con TensorFlow para lo que viene a ser justamente los dispositivos móviles y de IoT, Internet de las Cosas, y esos son los embebidos, ¿no? Cómo poder hacer este tipo de inteligencia y estas redes que pues necesitan gran cantidad de datos y poder computacional, pero en este caso utilizar la versión Lite, como lo menciona, TensorFlow Lite, y trabajarlo en estos dispositivos embebidos. Como también les decía, el tema de la producción, además que cuenta con un hub en el cual podemos justamente acceder a diferentes modelos que ya existen y que se pueden empezar a explorarlos y trabajarlos. Entonces, aquí está tensorflow.org, explorar un poquito la parte de la instalación, si la van a utilizar directamente desde sus servidores, desde su computadora. Como pueden ver, la comunidad en TensorFlow es bastante activa, existen diferentes lenguajes para revisar justamente todo esto de TensorFlow. Entonces, aquí podemos ver toda esta información. La parte de aprender justamente la biblioteca del código abierto, de todo lo que viene a ser el aprendizaje automático. También, como les decía, JavaScript para producción, Swift, incluido Swift, en todo lo que viene a ser en su versión beta. Y pues todos estos detalles con lo que vienen a ser los ejemplos. Después, avanzar en lo que es la parte del API. Aquí podemos ver las diferentes versiones también y cómo se trabaja, además de los recursos que podemos tener directamente lo que son los modelos, los conjuntos de datos, las diferentes herramientas, bibliotecas y extensiones, el programa de certificación de TensorFlow, que les mencionaba que José también ha sido aprobado en este programa. Podemos hablar un poco de eso más adelante también. El tema de los conocimientos sobre Machine Learning específicamente, donde ya se puede acceder a lo que son los recursos educativos para aprender un poco más sobre Machine Learning. Si es que ustedes también están haciendo lo que es enseñanza sobre estos temas, tenemos un buen material. Y algo muy importante que me gustaría resaltar es el tema de la inteligencia artificial responsable. Y pues conocer un poco más desde la parte de Google, cómo es el tema de las prácticas que van desarrollando en lo que es una inteligencia artificial responsable, o como se llama, un Responsible AI, con un flujo de trabajo, como ustedes pueden ver en TensorFlow. Entonces aquí habla bastante de este tema de responsabilidad, en todo lo que es inteligencia artificial, ¿verdad? Hay muchos más detalles sobre estos temas, pero también aquí está todo el tema de los datos, para evitar el tema de los sesgos, los bias, el tema para evaluar el modelo, en el enfoque del rendimiento, y pues también aquí resaltar el tema de lo que es el proyecto de People plus AI Research, PAIR, que eso también está desarrollado por Google, en el cual se hace bastante enfoque en que los proyectos, los productos que se van desarrollando como potencializados por inteligencia artificial, pues definitivamente no son solo un trabajo de ingenieros y de las personas que están haciendo el código, revisando los datos, sino también que debe ser un trabajo de equipos multidisciplinarios, que básicamente este guidebook tiene información bastante pertinente para redefinir el producto de inteligencia artificial más allá de lo que vendría a ser la parte de ingeniería. Entonces, como pueden ver, tenemos la parte de entender las necesidades del usuario, definir lo que es también el éxito del producto que queremos promocionar, el tema de la recolección de datos, los mapas mentales, el tema de la confianza que vamos a generar con el producto que se va a sacar, y pues otros temas más que son súper interesantes que podemos ir explorando para poder también crear esta mentalidad en las personas que no son de ingeniería, no son de desarrollo, la mentalidad y la conciencia de todo lo que viene a ser la parte de inteligencia artificial, que es súper interesante. Y también resaltar la parte de la comunidad. Como les decía, ya Joanna nos va a contar un poco más sobre esos detalles a nivel global, que ella trabaja desde la oficina en California. Y pues lo importante en los temas de contribución, en los temas de grupo, como tenemos ahora el TensorFlow User Group, y pues todo lo que se puede ir trabajando, bastante desarrollo también de la comunidad en GitHub y pues los diferentes anuncios, el mismo canal, Twitter y demás. Entonces aquí también está el blog. Les invitamos a que ustedes puedan conocer un poco más sobre la comunidad y toda la información que tenemos acá. Por ejemplo, también el tema de la contribución, cómo contribuir a TensorFlow, que va a ser súper interesante tener contribución desde Latinoamérica, por ejemplo, en español y pues los proyectos que se vayan desarrollando. Así que pues, para dar los primeros pasos en TensorFlow, conocer un poco más de los conceptos básicos, qué es, para qué sirve, en qué nos ayuda. Definitivamente también entender las extensiones, no solamente para proyectos que podamos hacer de manera local, sino también, como les decía, embedded, en producción, que ya nuestros invitados nos van a estar contando también un poco más sobre esta información. Y pues como les decía, aquí también tenemos diferentes ejemplos, desde lo más básico, si es la primera vez que están ingresando, lo que vendría a ser la primera red neuronal, sistemas de recomendación, ya un poco más avanzado, redes generativas adversarias, y pues casos de estudio, proyectos, que son justamente temas, proyectos desarrollados con lo que viene a ser la tecnología de TensorFlow. Podemos ver a nivel de desarrolladores, por ejemplo, aquí está enfocado al tema médico, al tema de la empresa, categorización de las fotos, al tema de investigación, un poco más enfocado a lo que es personal médico y pues bastante fuente de inspiración para poder aplicar todas estas temáticas. Entonces, otra vez invitarles a revisar un poco más de TensorFlow, a compartir con nosotros esta mañana de las diferentes presentaciones donde vamos a estar hablando, como les mencionaba, diferentes tópicos de toda la parte de TensorFlow, enfocados en inteligencia artificial. Y pues, sin más temas, invitar ya a Josh que está conectado, para que él también pueda comenzar su presentación de esta mañana. Así que, hello, Josh.
Hey, good morning. How's it going?
Good morning. We are super happy to have you here.
Yeah, thanks for the invite. It's good to see you.
Good to see you too. So, just this one in Spanish again. Josh, él trabaja en el equipo de TensorFlow en Google y también enseña sobre Deep Learning, sobre Machine Learning, y nos va a explicar un poco lo que es el tema de introducción al Deep Learning. Es una revisión general y pues entender un poco lo que son las redes neuronales artificiales, las diferentes técnicas, cómo funcionan, incluido lo que es el Deep Dream, y estos ejemplos con TensorFlow 2.0, así que ya empezamos con Josh. Okay, thank you so much, Josh, and we are ready to have your presentation.
Excellent.
Welcome.
Yeah, so basically, so this is going to be a quick intro to deep learning. And this might be useful if you've been doing machine learning for a little while, but maybe you're new to deep learning and you're wondering like what a neural network is and how it's different than things like decision trees and random forests and how to get started. And so basically, I want to get into what a neural network is. But first, let's just let's get on the same page with some terminology. And so let me make this bigger so hopefully you can see it. What we're looking at here is a diagram with 4 different circles. And they describe terms like AI or artificial intelligence, and then machine learning, and then representation learning, which deep learning is a part of. And this is very cool. I think you're going to like it. And then deep learning itself. AI is the most general term. And the way to do AI research is you think of a problem that people are good at, but computers are bad at. And that can be like riding a bicycle or programming a computer to play chess. And in AI research, you can solve it in any way you want. It doesn't say anything about how you solve the problem. And then when you have something like machine learning, that usually means that you're programming with data. And what that means is that you could be using something like a decision tree or k-nearest neighbors or logistic regression, and you're adjusting the parameters from a data set. And then you get into representation learning. And representation learning helps you work with high-dimensional unstructured data. So for example, if you want to work with something like images or text, one of the challenges with classical machine learning is that you need high-level features to feed into your decision tree. So a tree has trouble classifying images based on the pixels that are in them. And the tree really needs a higher level description of the features, like what are the colors, what are the shapes, what are the edges. And that's what you get when you use something called representation learning. So we'll come back to this slide in 1 second. What a neural network does, a neural network, and this is deep learning, a neural network automatically finds good representations for data. So here we're looking at a cartoon neural network, and the idea up top is we're feeding some pixels into the network, and maybe these are pixels from some image. And the pixels are processed by these different layers, and the idea is that each of these circles represents a neuron, and the first couple layers find features from the data, and the last layer classifies the data. So for example, the neurons in the first layer might be learning to detect features like edges. Those are combinations of pixel values. The neurons in the second layer are learning combinations of edges, because the neurons in the second layer are no longer connected to the input. They're instead receiving the output from the neurons in the first layer. And so they're learning combinations of edges, which could be something like a simple shape. And that means the last layer is classifying the data in terms of the shapes. And this is called representation learning. The basic idea is that the neural network is learning this hierarchy of features as it goes. And that enables it to work with things like images without you having to write complicated feature extraction code yourself. So basically, representation learning is a fancy way of saying it's a family of techniques that automatically learns useful features from data. And neural networks are by far the most successful. Another thing to mention is this is by far the most complicated area of machine learning, at least on this diagram. And it usually takes about a semester to learn. So if I'll show you how to get started today. And machine learning or deep learning rather, is really dense in like random concepts and names. It's not as complicated as it looks, but it does take a little while to get started with. Anyway, we can actually visualize some of the features that a neural network has learned. So what we're looking at here is a really cool diagram. And this is after we've trained a neural network to classify data. So maybe we started with a data set of thousands or even millions of images, and we trained an image classifier. After we have that classifier, what we're doing here is we're picking individual neurons, and we're finding an image that's representative of the patterns that neuron learns to detect. And each of these squares, there's 6 of them here on the left, each square corresponds to a pattern that a certain neuron is learning. And you can see that the neurons in the early layers are learning to detect things like edges. And as we move to the right, we're going deeper into the network. We have neurons that are detecting textures and patterns and even specific parts of images. It's really beautiful, and it's a little bit trippy too. We'll get into code in 1 sec. Another good thing to be aware of is that broadly, there's 2 types of data that you might be working with in machine learning. There's structured data, and this is the most common, but it's also the most boring. And it's also very important. Structured data is a fancy way of saying you have a spreadsheet, or you have tabular data that you can fit inside a CSV. And lots of business problems fall into this category. And when you have structured data, the key thing is you usually have like small number of features. So you might be talking about a patient in maybe a medical setting, and you might want to predict their risk of heart disease. And you can do that by looking at features like, I don't know, their blood pressure and their weight and what medications they're on and stuff like that. But the idea is that you have a small number of features that you and I can think about and we can reason about. When you have unstructured data, that's when you're doing something like image classification. And the issue is that if you're trying to classify a picture, what a picture looks like in code, it's just this huge array of pixels. And you and I, we can't really classify pixels or pictures in terms of the pixels in the image. We're not very good at that. So like when we decide if something, when we see a picture, we don't see the pixels, we see these high level features. And that's what a neural network does as well. Anyway, let's take a look at some code examples from TensorFlow. Let me see if I have any other slides. Actually, just kidding. Before we do that, let's take a look at what a neuron actually is. So this is a cartoon neural network. And let's very, very quickly at a high level pick it apart a little bit. So the idea is that a neural network is composed of layers. And these are the simplest type of layer. They're called dense or fully connected. And this is what you usually start your machine learning journey with. And the idea is that every neuron, which is a circle in the dense layer, is connected to every pixel on the image above it. And these gray lines represent learnable weights. And all of the learnable weights are going to start life as small random values. And we adjust them over time using gradient descent. The width of the layer roughly indicates how many patterns that layer can learn to detect. So this might be a variety of different types of edges. The depth of the layer indicates the depth of the feature hierarchy. So deeper neural networks can learn more complicated feature hierarchies. So the usual flow might be like edges to shapes to textures. And then if you have even like 50 layers, you might find a neuron that's detecting things like eyes or tails or fur on a dog, high-level features like that. It's a mistake to try and reason too closely about this. So unlike something like a decision tree, these neural networks are fairly opaque, and we can understand a little bit about what's going on inside of them, but our intuition is not very good. And that's because they're trained by gradient descent in this high-dimensional space, and they're hard to reason about. But anyway, let's take a look at what a single neuron actually is. And this is something we can understand all the parts very well. So here's a little cartoon of a neuron, and it's drawn in a couple different ways. On the left, you can see this block diagram, and on the right, you can see the equation written in two different ways. And it's the same equation, just depending on which you're more comfortable with. Anyway, on the left, we can see that the neuron is taking some inputs. And so here, x0, x1, and x2 correspond maybe to some pixels on an image. And each of these inputs is being multiplied by a learnable weight. And that's written by theta 0, theta 1, and theta 2. And these are the things that we're training by gradient descent. To make a prediction, a neuron multiplies all the inputs by all the weights, and we sum that up. And that gives us a single number. And basically, we can say if that number is greater than 0, then it's class 1, and if it's less than 0, it's class 2. So a single neuron is like a binary classifier. And we'll come back to this activation function in a moment. And here's another way to see exactly the same thing that's happening. So basically, on the left, we have like a little picture from an image, a little image. And we're seeing the pixels from that image. And you'll see this in code in a bit. And here we're pretending that this is a grayscale image. So every pixel has just one value. That's the pixel value. And we're pretending there's just four pixels on this image. To classify this image with a neuron, we unroll the pixels into an array. And that's what you're seeing here in this column vector X. And you see these correspond to the pixels on the image. The reason we have to have an array is that the dense layers that we're looking at are very simple. And they can only take arrays as input. They don't know how to take something like a square image as input. So we have to unroll this into an array. And then every input is multiplied by a weight. So these are the thetas that we're going to learn with gradient descent. And then to classify it, we take the dot product. So we multiply every input by every weight. We sum that all up. We add a bias, and we get a score. And we can say that if that score is greater than 0, in this case, it's a plane. And if it's less than 0, it's not a plane. So it's a little binary classifier. And here we're building like a little cartoon neural network that this corresponds to. And I actually have a mistake on my drawing here. There should be 4 inputs to our little neural network. And the reason there should be 4, not 3, is we have 4 inputs here. So just pretend there are 4 inputs. Now let's talk about activation functions. And the idea is that without an activation function, we're getting some score between positive and negative infinity. And sometimes we want to squash that to make it easier to work with. So there's a piece of math we could apply to this called a sigmoid. And a sigmoid, there's no machine learning function, or there's no machine learning. A sigmoid is just a function that takes some number and squashes it to be between 0 and 1. And so if you put a sigmoid on this, then we can interpret the neuron as producing a probability. If it's greater than 0.5, it's a cat. If it's less than 0.5, It's a dog. And there's other activation functions too. And I know I'm moving quickly through this, but I want to show you how we go from a neuron to a dense layer. So here's some TensorFlow code that you'll see in a sec. And here we're creating a dense layer with 10 outputs. And here there'd be 10 outputs on the bottom as well, or 10 neurons, or units. We use all these words interchangeably. And there's another activation function called softmax. And usually when you're doing something like image classification, one thing you want is you want to get a probability distribution. So here maybe we're classifying an image and we're not sure if it's a cat, a dog, a sheep, a horse, a zebra, or whatever, like 10 different types of animals. And we want to know the probability that it corresponds to every animal. And that's what this softmax activation function will give us. But anyway, here's how we go from a neuron to a dense layer. So the idea here is that we have, and here's the cartoon on the top that we're building up to. To go to a dense layer, all we have to do is add another matrix of weights. And when we add another matrix of weights, we're basically adding a second output to our layer. And now you'll see that we still have the pixels from the image. But when we multiply W and X with a single matrix multiply, you can see that we get two classification results. And so now we have a multi-class classifier. And the reason that GPUs are so popular for deep learning is that GPUs are very fast at multiplying matrices. And there's matrices everywhere when we're training and making predictions with neural networks. And they enable us to basically classify data very quickly because they can do many multiplications in parallel. Another trick you can do with GPUs is you can classify two images at once. So here, we now have 3 rows in our weight matrix. So we're going to get 3 outputs for each image. And we've also now added a second image to our diagram here. And we have a second column in X that corresponds to the pixels from the second image. And this means when we multiply W and X, now what we're doing is for 2 images at once, we're getting predictions for both of them in parallel. And we have a multi-class classifier that can do multiple predictions in parallel. And again, this is with just a single matrix multiply. And that's why GPUs are so great. And in TensorFlow, this is called the batch size, which is a fancy way of saying how many images are you classifying at once. And in TensorFlow, the batch size by default is 32. So this would have 32 columns. To build up to a neural network, we have to add one additional dense layer. And I just want to show you what the math looks like for that in a sec. So on the bottom, the math for one dense layer is basically matrix multiply, W times X. And to go from a dense layer to a neural network, it's a little complicated, but we apply an activation function G. And G could be something like sigmoid or ReLU, which is a different type of activation function. And then we multiply it by another matrix of weights. So what that looks like is we take the output from our dense layer and we apply a function like G to it. And G just modifies the output. So it could threshold it between 0 and 1, for example. And then a neural network is we multiply that by another matrix of weights. And there's different types of activation functions. So here you can see sigmoid on the left. I know it's small, but G of Z is this blue line here. And it basically just takes an input and squashes it to be between 0 and 1. And there's other activation functions that are used today for reasons of gradient descent, things like ReLU, which function more as an on-off switch. But basically, you can think about it as squashing a number to be between 0 and 1. The reason that we have to apply an activation function after every layer is that they enable the network to learn nonlinearities. And so basically, here you can see that we're trying to, what I'm trying to show you is that we have a data set with these 2 moons, and they're overlapping. We have the blue moon and the red moon. And without these nonlinear activation functions, we can't train a neural network to classify this data. It won't be able to. But when we have something like sigmoid, it lets the neural network learn this nonlinear boundary. So we always have to have an activation function after every layer. But just to make it super concrete, if you apply an activation function to the scores produced by a dense layer, all you're modifying is the scores themselves. So here we're applying ReLU just for fun. And I just wanted to show you, and you can go through this if you watch the video later, that it's only modifying one score at a time. And we have some links that I'll point you to at the end where you can get more detail on this stuff. And then a deep neural network is just basically one more layer. And so we sort of have this onion that we're building up. A dense layer is WX, a deep layer is, a neural network is WX followed by an activation, followed by another weight matrix. And then this pattern continues. So we just add another activation function and another weight matrix. And we go so on and so forth. And that's how we build up to a neural network. And then if you want to get started with this stuff, the best way to do it is on tensorflow.org/tutorials. You can go to Machine Learning Basics with Keras. And this is probably the best tutorial to get started with. And there's different ways to run these things. You can find them all on GitHub, but you can also open them all in Colab. So if we click Open in Colab, then you can run this tutorial right in your browser. And Colab, it's a free Jupyter notebook from Google Cloud, and it comes with a free GPU. And one thing you can do is you can enable the GPU. So if you go to Edit and then Notebook Settings, you can select a GPU. And if you hit Save and Connect, and you hover over Connect, you'll see that we're connected to some VM with GPU, which will help these tutorials run faster. And then basically, because it's a Jupyter notebook, you can step through it if you like. You can run the cells using Shift-Enter or by hitting play, and you can basically go through these and learn all about them. And we have tutorials for a lot of basic stuff, which is a great place to start, obviously. And we also have tutorials for some really cool stuff. So for instance, if you wanted to learn how to classify audio, so this would help you train a classifier to hear sounds like yes, no, left, right, up, down, you can do that. Or if you want to do transfer learning, this is a brand new one we just published, I think a couple days ago. That's why it has that little bug or that little sign that says it's new. But anyway, let's just take a quick look at this tutorial. I'm not going to read the whole thing to you. You can do that at home. But I just want to show you a couple key points and how it corresponds to the slides that you just saw. So basically, TensorFlow is a Python library with the C++ backend for speed, and we're importing it here. And then this is the fashion MNIST data set. And it basically has thousands of tiny pictures of clothing. And we're going to try and train an image classifier to identify different types of clothing. And it's a famous data set, so it's built into TensorFlow. And of course, you can load your own data sets as well. And if you want to load your own data sets, you can find out how to do that in this section here. So if you look at load images, this will teach you how to load a data set from disk. And you're going to download like a zip file of pictures from the web and then load it and train a model. But anyway, this data set is built in. And then basically, the word TensorFlow, a tensor is a fancy word for an array or a matrix. And flow means that we're basically processing matrices with a neural network. And so if you look at the shape of the images, you know, there's 60,000 images, each of which has 28 rows and 28 columns. And each image has a label. And here you can poke around with the shape of the label. So this tells us the first image corresponds to a 9. And the name for a 9 is an ankle boot. So that first image is a picture of a boot. And a really important skill in machine learning is poking around with the data, just so you get familiar with your data set and you know what you're working with. And if you look at the first image from the data set, we can see that it corresponds to that boot. And this is the default color scheme in matplotlib. These images are actually grayscale, and we'll fix that in a second. For different reasons, neural networks prefer small input values, and the pixels inside these images range between 0 and 255. But to train a neural network, we usually like the pixels to be between 0 and 1. And that's basically because every input gets multiplied by a weight. And if those inputs are very large, the resulting value can be very high if the weight's big. And that can cause problems basically for gradient descent. So by dividing by 255, we're normalizing them to be between 0 and 1. And here we can plot a few images from the data set. And you'll see that now we're looking at the first 20 or so images, and the colors are correct because we used this binary color map. So that's getting familiar with the data. And now we're developing the model. And although this uses just a small amount of code, it is complicated. So usually it takes about a semester to learn all these concepts, but already you've seen things like dense layers. And so the neural network that we're defining here corresponds to this diagram here. So it's the same neural network. We have two dense layers. So that dense layer corresponds to this one. And then we have an output layer, which corresponds to this one. And the numbers are different. And usually there's some numbers we can adjust and some we can't. This number we cannot adjust because this has to correspond to the number of output classes, and there are 10, so we can't change this. This number we can adjust, and I think on my slides it was larger. The bigger that number is, the more powerful the network, but the more likely it is to overfit. And there's no way to know in advance what the right setting is. You learn from time with intuition, and usually deep learning is very experimental. So we often, basically run an experiment with different values and see which works the best. But anyway, after you define a model, you have to compile it. And none of this is beginner level, but we're using our beginners API. TensorFlow has fancier ways of defining models too, that look more like object-oriented programming or defined by run. But here we're using sequential. All these models are trained with gradient descent, and there's lots of different gradient descent optimizers that do things like adaptive learning rates and stuff like that. But Adam, the good news is one such optimizer, and it's usually a good default. So you can get away almost always with just using Adam. This metric's accuracy is telling us that we want to see the accuracy while we're training this model. And the complicated part of this is the loss function. And when you're doing gradient descent, you have to optimize against something. And we could use a loss function like mean squared error that you might have heard of before. And basically what cross entropy is, this is a type of loss function that works like mean squared error, but it's better for classification problems. And sparse categorical, it's a way of saying that our labels are basically numbers. So that's, we went really fast through this, but basically the label, we have the index of the correct prediction. So the first one is a 9, the next is a 0, and then 0 and 3. If these were in a different format called one-hot encoding, we would have a different loss function. And although this is complicated, the good news is there's really like 4 of these things. And you learn about the details over time. So for now, I wouldn't worry about it. From logits equals true basically means that we don't have an activation function yet on the last layer. So if, for example, we had activation equals softmax to give us a probability distribution, then we wouldn't have, then logits would be false. But you learn about that over time. When you train the model, all of these networks are trained iteratively, and we're doing different rounds of gradient descent. And what an epoch is, that's a fancy way of saying we've used every image from the network, every image from the training set once to do a round of gradient descent. So the image has gone through the network, we've made a prediction, we've calculated our error, and we've wiggled the weights a little bit with gradient descent to improve accuracy. And over time, you can see that the accuracy begins low. And here it's actually 78%, which is good. That's at the end of training the epoch. When we started the epoch, when all the weights are random, the accuracy would be about 10% because there's 10 classes. And over time, the accuracy improves. And then the next thing we always do in machine learning is we evaluate it on the test set. And you can see that the accuracy on the test set is often a little bit lower than the accuracy on the training set. And that's called overfitting. And you can learn more about overfitting in all these links. And then there's different things we can do. Here what we're doing is, just to make it easier to see what the network is doing, we're taking our existing model and we're adding an activation function called softmax to it. And this is just so it returns a probability distribution. And now we're making predictions on all the images from the test set. And we're basically looking at the scores for the first image. And you can see that a lot of these scores are, this is scientific notation, which is why it's hard to read. But a lot of these scores are super, super small. And we basically classify the image by finding the score with the highest value. And that looks like that one. And we can find the index of the highest value like that. And we can check the prediction against the test labels to see if it was correct. And in that case, it was. Here we have, our goal is to see predictions for a bunch of images. And this is just a ton of matplotlib code to do some plots. So I'm just going to breeze through that. But basically, all this plotting code, it's really cool. It's showing us for, I think, the first 20 images or so, it's showing us in blue if it got it right and red if it got it wrong. And it's showing you the the probability distributions the network assigned to different classes. And you can see a lot of these, it's really confident because they were easy to classify. And you can see this one that it got wrong. I guess it was a sandal and it thought it was a sneaker. You can see that it was confused between these different classes. So that's pretty cool. And then there's some more code here that just shows you how to grab an image and make predictions. Anyway, again, the tutorial we just went through quickly is basic image classification. But you can, this is a great place to start, and you can try it at home. If you're interested in something like that, but a little bit slower, we just put a video on the channel, I think last week, which has similar content to this talk. It's just like an hour, and I go a little bit slower through neural networks and stuff like that. So it's the first video right now on the TensorFlow YouTube channel, which is youtube.com/TensorFlow. And let's see, what else can I tell you? If you're interested in more advanced stuff, you can look at a tutorial for, well, actually, so this is a great place to start. My suggestion for you is after you go through this basic classification thing, you could learn how to classify real images. And so in the image classification tutorial, which is under advanced and then images, image classification, this tutorial starts with a real world data set from a zip file. So this is very representative of how you would go about training an image classifier in the real world on your own data. And basically, what's really cool about it is these images are actually pretty hard. And the goal is to guess what kind of flower is in the picture. And the issue is that, you know, if you look at a picture like this, you see a bunch of, I think, roses. But the problem is, of course, there's all this other stuff in the image. And likewise, it looks like there's a rose or something here in front of this tree, but there's all this other stuff. So it's very hard to classify this. And basically, this will help you load the data off disk. Just like the end of this tutorial, it will help you display you know, some of the images, and then you can train different types of models to classify it. The most important thing you should pay attention to is this section called overfitting. And basically, if you create a very large neural network and you train it for long enough, oftentimes your accuracy, which you're seeing in blue here, on the training set will be very high. And this work here, we're looking at accuracy as a function of epochs. And basically, the longer you train the model for, the higher the accuracy on the training data goes. But there's a problem here. And if you look at this orange line, this is the accuracy on the testing data. And the issue is that you see the accuracy on the testing data is not as high as the accuracy on the training data. And this is a problem called overfitting. And it means that instead of, we want the model to learn like, oh, like roses are usually red or white and they have like petals. But if we train this network for too long, it basically memorizes the training data. And it says that, oh, a rose looks exactly like this. And that causes it to do badly on new images. And the way to fix this, there's different techniques you can use to fix this. And this tutorial does a really nice job of walking through them. One such technique that you can use to help with overfitting is data augmentation. Which is basically, even though these neural networks sound fancy, they fail on simple cases. Like they don't always understand that, like if your training set didn't have any examples of roses that were like upside down, and you tried to classify an upside down rose, the network might not know what it is. So in overfitting, in data augmentation, we basically rotate images from the data set and show them to the network again. Other techniques you can use are things like dropout that this tutorial will walk you through. And you can see that after you fix the model, you can usually train these networks for a little bit longer, which means you get high accuracy on the training set, but also high accuracy on the test set, which is what we really want. And then if you're interested in how you can produce images that look a little bit like this, the best place to start, there's different techniques, but the best place to start is with a technique called Deep Dream. And if you go into generative and then Deep Dream, this is a more advanced tutorial that will show you how to create a picture that looks like this. And I just want to give you a very quick intuition for how this works. And then I'll stop talking, and if you want, you can try these tutorials, and happy to take any questions, or we can end a little bit early. But basically, in Deep Dream, you start with a pre-trained image classifier that's been trained on like 1 million images. And you start with an image. And I just want to show you basically, TensorFlow has TensorFlow has lots of pre-trained image classifiers that you can download. And this is one such model called Inception, which you can read about if you want. And there's all these famous computer vision models, and you can do this with any of them. But basically, we import the pre-trained model, and there's a couple things we can do. We can use it to classify the image. Let me see if we have an example of that. We should. Okay, here we actually skip that step. But basically, if we classify the image, we feed the pixels all the way through the network, and we choose the output neuron with the highest score. In Deep Dream, though, we're not going to do that. Instead, we're going to feed the image through the network, and we're going to stop on a certain layer or a certain pixel. And we're going to record the outputs, the activations, which are basically like the features that that model has found. And what we're doing here is each of these layers in Inception has a name. And the name was put in by the authors to make it easier for us to reference them. Basically, Mix 3 and Mix 5, you can think of as those might be the names of like this. Let's just say it's the names of this layer. Inception has like lots of layers, but that could be like the last 2 layers in the network. And we're creating a model just to get the activations of those layers. So what we're asking is, if we feed an image through the network, how strongly was this layer activated? And we always, our goal is to find an image that excites that layer. And the way we do that is with gradient descent. And basically, there's 2 things we can do. And I know this is fast. Usually when we train a neural network, what we're doing is we're wiggling these weights to reduce the loss, to make it a more accurate classifier. And that's how you train a classification model. In Deep Dream, what you do is you start with an image that looks like this, and you adjust the image. So you use gradient descent to slowly modify the pixels on the image such that the activations coming out of a layer are higher and higher and higher. And you can do this for an entire layer or for a neuron. So for example, if this neuron, if we want to know what this neuron detects, we can create a loss function which says how activated is this neuron, basically how large is the number coming out of it, and we can adjust the input pixels to make that number higher and higher and higher. And that's what we're doing inside this code. And I know there's a lot of it, and it's a little bit complicated, but what's really interesting is it's not so complicated given the result that it gives you. And this is a pretty big deal. And so here we can see that those layers we picked, and we tried to excite the entire layer all at once, are learning to detect things like eyes and these weird little faces. And this looks a little ugly, and that's because we kept the code short and we didn't try and optimize it too much. But there's other techniques you can do basically to make the output prettier. And it's basically there's the takeaway from this. To learn about Deep Dream, you can go through some of the resources in this tutorial, which will walk you through a blog post like explaining what it does and how it works. And although it's complicated, what's really interesting in deep learning is that it's not so bad. There might be like 50 lines of code here, and it's 50 lines of code to produce a really interesting, beautiful result. And that's true of many areas in deep learning as well. So there's other types of models like GANs or generative adversarial neural networks. And here the goal is to synthesize an image that corresponds to this block diagram. So here we have block diagrams for basically a bunch of hotels. And the goal is to use a special type of network called a GAN to synthesize an image that might correspond to the block diagram. And again, like there's a lot of code here, but there's not so much code considering that we can actually end up with a fancy type of network that actually produces basically hotel images, which is kind of crazy. So yeah, it's a really rich and interesting field. The way to learn about it, and again, it takes about 6 months. Here's 3 books you might want to check out. The one on the left is still being written. It's called Deep Learning with Python 2nd edition. And that's the easiest way to get started with TensorFlow today. And you can actually buy it, although it's still being written, and you'll get access to the chapters as they become available. The second book in the middle, it's hands-on machine learning, and it's very important to get the 2nd edition. Basically, there's 2 versions of TensorFlow. There's TensorFlow 1 and TensorFlow 2. TensorFlow 2 was released a few years ago, and it's much easier to use. So what you want is definitely get the 2nd edition of this book because it teaches the latest version of TensorFlow. And what's nice about hands-on machine learning is that if you're new to machine learning in general, the first half of that book uses a library called scikit-learn. And it starts with things like decision trees and whatnot, and it's excellent. And the second half uses TensorFlow. And then there's a really nice book that's free. It's called the Deep Learning Book. And this is basically an academic textbook. There's no code, but there's a lot of like papers and math and diagrams. And what I usually do, I would read one of the others, doesn't matter which, they're both really good. And if you want like more detail, like if you want to know the math behind gradient descent, then the Deep Learning Book has basically, you can read the same chapter in that and it will help you out. So that's a really solid learning journey. Yeah, so I'm happy to take any questions, and if not, I'll stop here. And again, basically the next steps, youtube.com/TensorFlow if you want like a longer version or a slower version of this talk. And then I would play around with the tutorials on the website, tensorflow.org/tutorials. And if you want, you can check out one of these books to learn more. And so, yeah, that's all I've got for now. I'll stop here.
Great, thank you so much, Josh. It's really appreciating all the overview we have having, as well as the resources. I know people were not asking questions directly, but finding the books and the sorry, and the tutorials. So great. Thank you so much for your time and for supporting this event on Saturday morning.
Yeah, thank you for organizing it. Hopefully see you in person next year at the latest.
Oh yes, hopefully.
Yeah, yeah, much more fun when we can do like events and conferences, like so we can hack in a room. Zoom is tough, but yeah, we're doing the best we can.
Yeah, in the meanwhile. Thank you so much.
Thanks again.
Bye bye.
Bye.
Muy bien. Ahora tenemos a Bianca Ximenes. Ella nos va a presentar el tema que es el Machine Learning en producción. Ya les contaba un poco, ella es Product Manager de temas de inteligencia artificial en Guppy. Además es Google Developer Expert en Machine Learning. And hi Bianca, hola. We are so happy to have you.
Thank you, Leslie. Thank you, everyone.
So welcome, and the stage is yours.
Okay, I'll get right down to it. Just hold on a second. Just let me see. I'm using a computer that's not my own. So I'll override the sharing, okay? Let me just see if I can get it to work. Almost there. Okay, I'm gonna need to leave because there's like a security issue here. I'll leave and I'll join again, okay? Real fast. Hold on.
It's okay, thank you.
Leigh, estás en mute.
Perdón, mientras tanto vamos teniendo un par de preguntas. Josh, I don't know if you have some time for one more question. Anyway, the question is about what do you think about MIT Course Edition 2021? Lo vamos a compartir con Josh si no nos responde ahora, pero personalmente he estado viendo los primeros cursos y creo que son muy buenos en temas introductorios, además que los proyectos que van compartiendo son bastante prácticos. Creo que es una de las mejores maneras en realidad de poder aprender y porque estás practicando, ¿no? Todos esos detalles, así que pues sí, también los recomendaría. Tal vez si ustedes no lo han visto, está aquí el tema de YouTube, ¿no? El tema de lo que viene a ser los cursos del MIT. Entonces, tenemos de vuelta a Bianca. Igual yo les dejo acá en el grupo, en el chat, el link directamente para el curso. El curso de Deep Learning desde el MIT. Bianca, welcome back.
Thank you. Can you see my screen, everyone?
Yes.
The ML introduction slides? Okay.
Welcome, and yeah, we are here to hear you.
Okay, cool. Since we're not that many people, I'd like to make like more of a conversation. So if you have any doubts, I don't have two screens right now, but you can interrupt me and ask questions, okay? So I'm here to talk today a little bit about my everyday life, which is working in a big company, an HR tech, we call a human resources technology company. And I'm going to talk a little bit of our challenges of building a product of machine learning for millions. I'm not going to introduce myself because Leslie already did a great job. So I'll just get right on down to it. So nowadays we have this huge, like we have kind of two currents that some people love machine learning. And I think that here we're amongst a lot of lovers of machine learning and a lot of people hate it. And there are good reasons for like both sides of that. But let us see a little bit of the issues, right? Every time we talk about machine learning, there are so many different things that might go wrong. And whenever a model goes wrong in production, it has huge repercussions. So one of the things that happened to Amazon the past years was that they had to scrap an AI recruiting model because it showed bias against women. We have the China social credit system that records dissertation cheating and then lowers your rating and your possibility to get credit, to travel, to get a passport, to even people you can date, to jobs you can get, you're eligible to get. And then we also have GPT-3, where people are asking themselves whether the model will replace real people, will replace software developers. So there's a lot of things, like a lot of fear and a lot of questions around it, right? But like the first thing I'd like to say is that software engineer is obviously different from machine learning. In the means that software engineer usually builds tools, right? Software engineer gives us tools to use, and we are the decisors, like we are the people that make decisions. And maybe that's the reason why whenever something goes wrong with machine learning models in production, people get so afraid, because usually when we make a machine learning model, we're making something to make decisions for us. Sometimes we're what we call in the loop, and we're working together. Sometimes we're on the loop and we just like give a check and see like if the final results make sense. And sometimes we're out of the loop and the system makes all kinds of decisions without us even knowing, which is the case of the financial system, for instance, where microbots make transactions every day, and like more than 50% of transactions in the New York stock market comes exclusively from out of the loop machine learning systems. So these are two different things. There are two different purposes. And one thing I also like to make clear is that this is not better than the other. You know, those are two things that we need as a whole. So we need the tools, we need models to help us. And there's no such thing as, well, machine learning is harder or better or whatever. So I'm not sure like how much you know about machine learning. Usually when the event is very specific, such as TF Everywhere, we're more, we have more people that already work with that. But in case you are a curious person who's here just to get a little feeling of what AI can do, I must tell you that like we have all these expectations of AI because of what we see. Usually we have a corporeal AI, something that has a body, right? And someone, because it's like a person in the end, but that's very communicative and generalist, that like can do and deal with pretty much anything, that's very empathetic, and that can plot like plans and new futures and things that have nothing to do with what we wanted to do right now. And that is sentient, right? Like has a feeling of self and what the person can do or should do, and has feelings. But AI is not anything like that, right? AI is pretty much what you just saw in Josh Gordon's presentation, which is, well, we can try to teach patterns, right? We're very good in teaching patterns, and the deep learning models are very good in understanding those patterns and making it, bringing it down to real model decisions and generalizing it to the bigger scale. So it's nothing like that. But let's take just a deep down look, and I'll bring you the where I work in, right? Like the scenario I work in every day. So when we're recruiting, and I am sure that everybody has been in this scenario before, if you're not recruiting someone, like trying to hire someone, you've been there as a candidate, right? You've subscribed and you try to, like, you join the process and you try to get a role and start working for a given company. And the thing is that I started noticing, because I was hired as an AI product manager, I started noticing that a lot of problems we had, and like the way people do things, is very different from how they do it when we provide them with deep learning models. And here's why: is the way that people think, right? So people in recruiting, they're very used to like standards and criteria that serve as a cutting the sizer, like, well, this person doesn't make the cut, so I'll just eliminate them right away, and not really going down and understanding what the person has. And they have a lot of expectations of where you should have studied and how many years of experience you should have had. They use a lot of filters, and they're usually very sensitive with time, meaning that they prefer to look first, the people who subscribe first for the job opening, even if they have nothing really to do with the job opening in the end. So what we do with Gaia, which is our AI, and this is like our attempt of personificating the AI, giving it a kind of feel, right? A kind of that looks like an entity, not a person, but an entity. We work with this recruiting hiring specialist. We've trained it with over 4.5 billion words and sentences. And I can't give you a lot of details on our stack, but TensorFlow and Keras is there. We have over 35 million applications for different job openings, and it is a combination of ranking models and neural networks. So this is pretty much what happens. Like, we have first a model to identify the language, the CV and the job opening is in. We send it down to a ranking model. We use a lot of things, but XGBoost is one of them. We have other two, nowadays we have two, we're attempting to have more neural networks. One to understand like job name similarity, and another one to understand proximity of meaning between the candidate's content and the company job description. So we use that as inputs for our ranking model. But these, even though they're just like, each one of these is just one feature, and we have 140 features, these are usually the most important features we have in the ranking model in the end, just for you to have an idea of what we have. So we've created Gaia to rank and recommend candidates' resumes to a job opening according to what we call an affinity, which is pretty much what Google does when you search for something in Google search. Like you search, you put down some keywords, and then they rank results according to a bunch of things that they can really tell you, but a bunch of things such as like if the connection is secure, and how many people access that result and how much time they spent there, and like relevance, right? A lot of things that pertain to relevance. So for us, the affinity considers the mathematical and linguistic similarity between the candidate's resume and the job description, amongst a lot of other factors. So we're the biggest HR tech in Brazil. We have 2.5 million new applications every month, and we've hired 25,000 all in September 2020. We have to make 7.5 million new score calculations a week because we have to calculate a score in order to make a ranking, right? And we had over 500 hours of training, model training a month. So these are just like specs for September and last year. And Gaia provides great results, like 65% of people hired are in the top 10 results. We can really understand who's really more likely to be hired and put them up there. And we've saved 13 years of resume reading in 2019. If people were to read every resume, which usually does not happen. So we at least guarantee that every resume will be processed and information will be considered in the ranking process. So now, like, this is all very nice and all very cool. And this is why I started working there, because the problem just seems so great, like the impact really that we make. But when we need to go behind the scenes to understand a little bit more of our challenges. So I'm going to talk today about, like, very briefly about 5 challenges we have when we're trying to serve models and put models in production for millions of people. So the first thing is to get qualified and current data. The second thing is to understand and reinforce behavior. The third is to deliver value to the end user. The fourth is making users understand the effects of what we're doing and explain what we're doing. And the fifth thing is to track and monitor results. So the first thing is to get qualified current data, right? If I get data that is very, like, that's kind of old, I'm not going to have an accurate model probably, because it won't be descriptive of what actually is happening right now. Like, it won't be descriptive of the phenomenon itself. So for instance, we have this thing we call a stream of ground truth. We don't have that at Guppy, and we're working on that. But for instance, this is Netflix, right? And this is Spotify. Whenever they're making you suggestions about movies, you can get in there and rate it like thumbs up or thumbs down. And at the same time, we have at Spotify, when you're streaming music, and this is much faster even than Netflix, you can say, like, if you want to skip it because you didn't like it, or if you really loved it. And then you let the algorithm know real time what's good for you. And based on that, they can optimize with current trends all the time. So it's very important when you think of a machine learning system that you consider how you're going to get ground truth, like a stream of ground truth. How are you going to build that? How are you going to get information that is up to date every time, pretty much every day, essentially, and, like, if you can, every moment, and how that is important to our model. We suffer a lot at Guppy because we didn't conceive of that. We didn't consider that when we first built our model. So we take a long time to get the data in order to learn. So this is one thing that, to me, is very important when you're considering. And it seems like something very silly, maybe like thumbs up, thumbs down, or I like and I don't like, but it's something that is very important in order to guarantee that the model is relevant and it's getting real data all the time. So we started training this one model here, which is a named entity recognition model. I'm going to show you a little bit more of it later. But, like, we started trying to at least understand the little blocks of information we have in job openings, to understand if the job opening is a good job opening or not, and to see if we can help improve the quality of those matches. Because whenever you write better, you give me more information so I can find better candidates for you, like for your needs. Doesn't mean the person's better or worse. It means that it's more fitting of that specific opportunity. Well, we started to having to do that in order to understand, to curate our data and improve the quality of the pairs we used for testing. So we have this this step now on our pipeline, on our machine learning flow, in which we get the results of what happened in a given process, and we check for the quality of that job opening, seeing if it has at least most of those requirements, and use it to test it because we realize that it gives us better results. But this is a way of curating and improving the quality of the data you serve your model for training and for validating later, obviously with separate data sets. But this is something that we didn't do before, because we figured that whenever people made the movements, it would be enough for us to know that we had a great result, you know? And we realized that it wasn't that way. It wasn't so. So we started to annotate a lot. And this is something that people usually don't like doing. And data scientists sometimes there are people that usually get paid well. And this is a really boring job to do. So we try to outsource it to mechanical Turks and everything like that. People who do this kind of annotation for you. But for a whole month, we made this task force inside our group to annotate a lot of pair quality. So like, for instance, we have this job here, a description for a finance analyst and this candidate. And we had to read everything and say if we considered it similar or not. We had similar, not similar. It was like unresolved and need more information. So we started annotating thousands and thousands of resumes to improve the quality of the data we were serving our model. And annotations are so important because of the labeling, and they're very important in supervised model or semi-supervised models. And also to guarantee that you're putting quality material inside your training, inside your models. So in the end, keep in mind that we had 5 people annotating throughout a whole month, and we had over 3,000 annotations team made by hand, which looks like a lot, but we wish we'd had more, you know? We spent a whole month on that task force and we got 3,000 annotations. So it's something that is time consuming, but it's so much better when you do it yourself, because you know what your model needs and you know what you're looking for. So if you outsource it for someone else to do, maybe they won't be thinking the way you should think. So we had this huge guideline on what we should look for and what we should consider in order to make it similar or not, in order to help our models learn. So annotations are something that I cannot stress enough how important they are for good models in production. Another thing is error analysis is another thing that data scientists usually don't like to do because it has a lot to do with simple statistics. But it's so important for us to understand when our models went wrong and when they didn't behave the way we expected. And this we were troubleshooting here one of our neural networks that we call Sherlock. So we had so many cases it behaved exactly like we wanted. In other cases it didn't help a lot, but it wasn't a bad result. But in some cases actually they had false positives and false negatives going on. So this is very time consuming also, but it's something that you have to do to understand. Usually is information that's lacking in your model. So what type of information I lack here, and why did it make that kind of choice? So you have to question yourself all the time, and you have to provide a little bit of explainability that we'll talk about later. But explainability is also very important to the team. It's not only to the user. So another issue is to understand reinforced behavior, right? So again, bringing the context of error analysis, we're trying to understand these are the ratings, the ranking ratings of people who were approved and got a job. And these are the ratings of people that were eliminated and didn't get a job. And we realized that, I mean, there are differences, definitely, and beyond 70% of similarity, we have more people here than down here, right? But we have a lot of people in the 50s and 60s. So essentially, they're not very different from one another. Like, there are two different groups, but they're not that different. But part of them got the jobs and part of them didn't. So we realized that one of the problems we had was that only 40% of the candidates were moved, which means that they advanced in the process. And I think maybe you can relate to that when you registered for a process and people didn't give you any feedback at all, or you never really seemed to get ahead of the process. For some reason, someone looked at your resume and they decided not to move you ahead. So 60% of people who join processes and hiring processes, they actually never get moved. So we don't have as many examples as we'd like and as we need for people who are not a good match for that job. So this is a problem in itself, because you need examples of everything. Otherwise, your model will underfit, probably. And only 50% of job listings were marked as finished. And we only send, and this is the type of problem we had when I told you about the streaming, the stream of ground truth, right? So only 50% of job listings were marked as finished. And we only send the information to Gaia to learn when the job listing is done. So we're only training with 50% of what we could possibly use, you know? So all those things make you understand that, like, it doesn't, if I make a pipeline that depends on people closing up the job descriptions, the job opening for me to learn, I'm going to take a really long time to understand what happened. And at the same time, if people are only moving 40% of candidates, I have a lot of information that is not being used and is not there for us to actually assess and use as a means of learning. So part of our analysis is how bad or how good your model does. And part of our analysis is trying to understand how people behave and how you can use it in your model. And this is so important. Another thing that we started doing was understanding, like, the type of requirements that appeared, like, on the job descriptions. And we started realizing that for some type of openings, mainly for people who sell, like, commercial areas, people would ask a lot of soft skills, which are like high energy, initiative, work as a team, resilience, and interpersonal relationships. So, but usually people don't put that in their resumes in Brazil. In the United States, I know they do, because I've seen a lot of that and I've participated from a lot of processes. But in Brazil, people don't actually do that. Usually they're very straightforward about what they did. And we don't have, like, a cover letter or a motivation letter for people to understand why you want that job. So this type of information that people really require in job openings, they're not there in the candidate's resume. So it's not something I can look for and understand and make a match. So we started asking ourselves also, what type of value do we deliver in these openings? Because our rankings are not as accurate for these types of openings as they are in other ones. So this is another thing that we have to understand. Sometimes we're not delivering, and this is very common. We are not delivering the same type of value to all our clients. And we're not delivering the same type of value for everybody who uses it because of differences. And sometimes these differences are significant in how people use your product. So it's something that really has a lot of space, gives us a lot of space to improve on what we're doing. And in the end, when we did all that sifting, we realized that 5.6 million only out of 35 million applications were useful for training and validation because of quality, of how the process went, how many people were moved. And now it's like we only have 1/7 of what we could actually have to train, like, a good model, an accurate model. So a model that we use this 5.6% million of curated data perform much better than the one we had with 35 million applications. we didn't use all of that for training, but you get the idea. It's like curated data is so much better than like a bunch of data. This does not always help. And concerning delivering value to the end user, right? We have here a story cycle, you might know, which is the crisp DM, we call, which is the steps we have to follow in data mining. So you have business understanding, data understanding, preparation, modeling, evaluation, and deployment, right? And this follows this cycle here. The thing is, when you say deployment for ML, usually you don't mean that you're deploying for users. Like it doesn't get there. It doesn't reach your final users, actually. And why is that, right? The thing is, usually what we deliver as a machine learning team, there are APIs or endpoints, correct? So APIs and endpoints are something that do not actually reach actual users in the end of the chain. We really need a software engineering team to plug it in and to serve that to the actual users down there. And this is something that a lot of machine learning teams do not consider important, like having a software engineering team. But this is so important for you to serve what you actually need and gather to the actual users in the end. Otherwise, you just end up with a bunch of APIs and really cool things you did that nobody will ever use. And it's not because what you did is not important or not interesting. It's just because that they cannot access it, you know? So every machine learning team should consider having software engineering teams and should consider how they work together in order to deliver value to actual users down there in the end of the chain. This is how like big companies such as Netflix and Spotify and Google work. And that's what we're trying to do right now at Comparte too. A subset of that problem is the thing of serving the model to millions, right? And I'm sure that all of you that heard about machine learning have heard of Kaggle, which is this platform for competitions, right? Where big companies such as Netflix was the most important case, the most famous case that went down at Kaggle, but there were also like NASA data sets and so many different data sets. And you go there and you compete with other people in order to try and deliver a better model. And one thing that always happens in Kaggle is what people deliver and actually wins a lot of competitions is never put down to production. So we have this type of questions in Quora and Yahoo Answers and everything. So what was so complicated about implementing the Netflix Kaggle competition winning method? And I just love this answer because it's very straight to the point and very true, which is the winning model is based on 100 million ratings, which while Netflix has 5 billion ratings in production, the engineering effort to bring that model in production is costlier than the business success from the accuracy gain. So we have this really great model, but it only has 100 million ratings, and Netflix has 5 billion ratings. So it's the cost for infrastructure and for adapting your infrastructure to justify and what you would gain in the end is not worth it. It's not worth the cost. So you leave a worse model in production, but at the same time, you have something that can actually deliver some value, because otherwise this would not be feasible, like economically viable for Netflix to implement. And this is something that happens a lot in machine learning. For instance, and now I'll bring you like our case. We have this model that I told you about, right? You already seen a little bit of it, which is the named entity recognition model. We use, there are many approaches to that with AI and with regular expressions, with machine learning and with deep learning. We use a deep learning model. But we wanted to use that input as one of the deep neural networks that got inside our ranking process. And we could do a lot of other things besides plugging it in the ranking process as a feature. We could help writer better descriptions and tell people like, well, you said the information level you wanted, but you didn't specify what type of information is interesting for you. Or you didn't say any skills at all. You only put soft skills and all those types of things. So it could help write better descriptions. We could give qualitative feedback, which is a pain because I think that as candidates, we've all been there, but candidates usually don't get feedback when they are inside a process. You get feedback when you get the job, right? But when you don't, you usually don't get any feedback. So this is something we could do for candidates. We could see like, well, the people who were hired had that type of information here, and the people who weren't didn't have this. So we can send out to the participants, the candidates of a process, what is missing, like who was hired had and what they didn't have. And we could create an upskilling track. Like for instance, now I'm a software engineer, but I want to move on to data science. So what can I do? And like, I can understand what is required for us to change and for us to make that migration happen. So it's really cool, the number of things you can do with that. I'm really excited about that. So we trained her with 5 million pairs. We had an 82% accuracy in the end with a 13% loss, but it has been ready for the past 7 months and it's not still in production. So we were able to do nothing really with that because our infrastructure currently, our stack does not support it. So we're changing a lot of different things. Like we're making an ETL, we're doing a feature storage. We are doing a lot of different things to make our inference faster and our whole stack able to support another deep neural network that you plug in part of the stack as a whole. So things like that happen. You research a lot, and then in the end, you have to think of a way to serve it and how you can make it get there and actually change the product. So now this is what we're trying to do, like divide it in a research, experimentation, and development team, where we have data scientists researching, data engineering, Python developers, and experimenting, and data scientists as well. And finally, in the development section is the software engineers I told you about. Like we have the designer here, like kind of in the middle, to understand how people do, what people do, and how we can make the stream of ground truth come, and how we can understand how people behave in order for us to get better data and timely data. And here in the end, we have what people who serve this model to actual users. Another challenge is to explain effects and results. So 80% of customer contacts want to know like the features and weights of the model. So usually usually it's me, right? Because I'm the product manager, but when I get any type of inquiry from clients, it's like, what are the features you're using? And people don't even really know what features are, but they really want to know like what the model is looking at, right? And what are the weights? Like what is the importance of the relevance of this given feature? And that changes a lot according to the process they're leading. But we started a while ago, like 2 years ago, we started using Shep, which is a very tried and true way of providing explanations to your model, feature by feature, which is the Shapley additive explanations. And we started to understand like what type of features lower the ratings or lower, and I don't know, like improve the ratings for someone. And we don't show that to anyone because that's not really like, Shep is really, it's something more refined mathematically, so it's hard to explain like that. But you can say that, well, numbers of years of experience was something very relevant in this case. So that's why this person ranked higher than this other one, you know? We also have Lime, which is another tried and true method for explanations. And we're trying to understand like what type of words are a match and are, like have a positive impact on the rating of the person, and which types of words are not positive. And in the end, like I won't get deeply inside that, but Lime and Shep both have different characteristics and they complement each other very well. So, I mean, usually people, in my PhD, I'm researching that, like how many people actually concern themselves with providing an explainability model or alternative for their work. And usually that is not done. So by all means, start somewhere. And I'd say start with Lime. because it's easier to implement, it's much less costly. But like, if you can do both, if you can do more, it's better, because they will show you different aspects of the same phenomenon, and you will have more information to kind of understand what's going on there. And you really need to understand, because you're letting your model loose in the real world and it's making decisions. So you better look into it, right? So translating that to everyday language, like these types of results from the model, from Leigh and from Shep, this is really hard. Like, how can we translate that to the end user, right? This is also a problem that we have to concern ourselves with, because otherwise people won't trust what we're doing. And if they don't trust what we're doing, they will not use our models. So this is like a snapshot of a real process that I erased here, the number of the candidates and everything. But we started trying to help people understand with grouping features by similarity, like experience or profile or formation and things like that. And we put badges for people to try and understand what it was relevant in that decision. And we thought that was really cool. But then we have started having a lot of problems. Like, so for instance, why is 2 better than 3? Because people would be like, well, the person who ranked 10 had 2 different good things in their resumes. And someone who ranked 13 had 3 things that were good in their resume. So this is really hard to convey, because relevance does not mean that, I mean, having 3 things that are relevant does not mean that those 3 things were as relevant as another 2 things, you know? But this is really hard to explain to the user. And we need to figure out a way to do that. We're working on that, and we still haven't figured it out. But why is the test relevant if I made no test and the person hasn't taken it yet? So tests are usually things that really improve a person's rating, or a person's rank. So sometimes what the model does is, if you have someone who's really good, but they haven't taken the test yet, and someone else has, they will be lower in the rank. But if you made no test and the person hasn't taken, but the model knows that when they take it, probably they'll perform well, but it needs the data. So it's something also difficult to explain. Another thing is, people thought it was a quick build checklist. So this was really problematic, because in cases like this, for instance, like people would be like, here you have compatible formation, like people are here is good. Knowledge of other languages. So people would look at that and be like, candidate 13 has knowledge of other languages, which mean that the other ones don't. Like, people cannot speak English or Spanish or any other language. And this is not the case. This stands for relevance. This does not stand for what people have and what they don't have. So this was also another thing that we learned. We need to find some way to heuristically convey that in design for people to understand what we're trying to actually tell them. And finally, because also I'm in the end of the time, we have tracking and monitoring results. But we have this really nice research that was made here in Brazil about how often ML projects get delayed. And people would be asked, like, how do you manage ML projects? And a lot of people use Scrum or Kanban, which are not actually ideal to monitor and accompany, like to follow up on machine learning products. But like, this is still the majority of what people use. And actually we also use that at Guppy, because I was not able yet to convince that this is not the ideal thing for us to do. But we have so many challenges concerning them. Like, a lot of our projects get delayed, like well over 50%. We manage projects with frameworks that are not ideal and not specific to machine learning. And this is pretty much how, this is not our lead time chart, but this is pretty much how a lead time chart works for an ML project. So it's nowhere near as neat as it should be. So we don't even use that as an indicator in our team. At least we were able to convince people that this was not a good way to find out if we were performing or not. We have a lot of problem-specific issues too that I can really tell you everything about it because there are so many. But one thing when you work with text is the out of vocabulary terms. So you have a lot of things that sometimes are typos, sometimes are things that people forgot to put some space in between. Sometimes are other, like there's a whole lot of different things that the model doesn't really understand what it is. And at times, if there are too many of these words, your model can start making decisions based on information it doesn't have. So this is really, really complicated. And finally, in order to monitor, like we have Metabase also to monitor like production metrics, and we use Grafana, and we use so many different things that like I think most people already use. So I brought here like 3 different things where you can try to track and check what you do, which is weights and biases. I don't know if you use it, but it's a way to track experiments. It's like GitHub for machine learning experiments. And it's really nice because you can see what you did here. Like you can plot different models you trained and see how they perform against each other, see like their error rates and how many people they put down on the top, they put up in the top, and all those different things. And it's really nice to check that, like, and easily to compare. And it also stores every experiment you ever tried out. So it's something that is good for you to keep track of and to understand like the key metrics. I recommend a lot like this type of, if you want to understand more about ranking and the error metrics that Josh even mentioned in his talk, we used NDCG and MRE, but there are a lot of things you can use. So I really like recommend that post from Medium. We also use Streamlit as a way to plug in, like to do annotations and to plug in a lot of different explainability results. Like we serve Lime there, we serve Shep there, and a lot of different people can use it. And I can also use it as a project manager, so it helps me out a lot. And we use Prodigy to kind of understand and help us with our active learning and annotating training models. So like, just for you to get an idea in the end, like in September, we overperformed. 86% of hired people were in the top 10 positions. And we don't still know exactly why. Like we monitor a lot of things. We do a lot of different experiments. We have so many different trackings, but, and we provide explainability with more than one model, but still we don't know exactly why some things are like they are. But this is part of the challenge, I think, and this is part of why ML is so exciting. So if you're still interested in that, there is this really good presentation about from Jan's class in the PyData from Amsterdam, where he talks a little bit about monitoring models in production too. And I mean, we still don't have all answers and work is ongoing. This is a tentative talk, but I hope to have conveyed to you like the different challenges and the I don't know, the high stakes of working with ML and what it's like. Thank you so much for your attention.
Thank you so much, Bianca. It was really nice to know about your job and also to understand a bit more of practical ML. We have a question. It says, Sandro, in some way, can you use this model for employee attribution?
Employee attrition is like turnover, I think, if people are leaving, right? Not this model. This model does not have the enough, it doesn't have predictive features of employee turnover. And I'm actually, like, from an ethical standpoint, I'm not in favor of trying to predict turnover of employees with models, because it's essentially what we would be doing. I don't know if you've seen the movie Minority Report, but to me, it sounds a lot like that, because it's like you're trying to predict whether a person will defect like from the job or not based on the information she or he has on the curriculum and on the tests they make throughout the process. So you will end up punishing people that would not leave the job and that would not be poor performance because of some pattern that you would find. So this is not ideal because the features are not predictive. And if they were, I don't know. I don't think I would recommend. I think that we have so much responsibility with what we do in machine learning that there are some things that even though they're really cool to make, and clients ask me about it all the time, and I have a huge time like convincing them why they shouldn't do that. Even though it's cool and we can do it, I don't think we should. So that's my point of view.
Okay, thank you. Thank you so much, Bianca. It was so nice again to have you here in the TensorFlow everywhere. And yeah, thank you till next time.
Thank you guys. Thanks, Leslie, for the invitation and hope to see you soon.
Yeah, sure.
Bye-bye.
Bye-bye. Ok, continuamos con las presentaciones. Ahora tenemos un amigo desde Bolivia que nos va a presentar el tema Desplegando tu modelo de TensorFlow como un servicio en la nube. Ya está acá conectado con nosotros José Laruta. Muy buenas tardes. Bueno, les contaba al inicio del evento, José Laruta pues es uno de los pocos en Latinoamérica que tiene la certificación como TensorFlow Developer Certificate. José es ingeniero electrónico, también es desarrollador de software, full stack, y tiene bastante experiencia en software empresarial, sistemas distribuidos, robots interactivos, y también da clases en universidad sobre temas de inteligencia artificial. Así que, José, muy buenas tardes, y estamos muy felices de tenerte aquí hoy.
Ok, gracias a ti, Leslie, por la invitación. Bueno,
adelante.
Ok, entonces voy a compartir mi pantalla. Bueno, una de las cosas que más me va a gustar, digamos, de esta charla es que se va a conectar demasiado bien con las dos charlas anteriores. La primera, en la que se hablaba mucho del inicio, de cómo iniciar en Deep Learning, cómo poder explorar los primeros modelos, los primeros pasos. Y la segunda, de ya una aplicación que se está desplegando en producción, que está teniendo bastante éxito. Y lo que voy a hacer aquí es básicamente poder conectar esos dos conceptos y mostrarles a ustedes de una forma bastante demostrativa cómo desplegar un modelo de TensorFlow como un servicio en la nube, ¿sí? Bueno, Leslie habló un poco acerca de mí. Yo soy desarrollador y también me gusta enseñar acerca de inteligencia artificial. Y bueno, vámonos directamente a la agenda, ¿sí? A lo que vamos a ver en esta charla el día de hoy. Lo que quiero mostrarles son estos temas, ¿no? En primer lugar, vamos a hacer un repaso súper rápido de cómo entrenar un modelo de TensorFlow usando más que nada el API de alto nivel que es Keras. Voy a introducir una herramienta para elaborar servicios web, ¿sí? En este caso estamos hablando de APIs REST, que se llama Fast API en Python. También vamos a introducir el concepto de los contenedores Docker para poder desplegar este tipo de aplicaciones. Y al final voy a introducir este servicio de Google que se llama Google Cloud Run, que nos va a ayudar a conectar o a utilizar un contenedor Docker con nuestro servicio con Fast API y nuestro modelo en TensorFlow. Nos va a ayudar a desplegarlo en la nube, ¿no? en un servicio que vamos a poder accederlo desde la nube. Y es bastante sencillo, ¿no? Y eso es lo mejor. Y al final algunas recomendaciones, tal vez alguna discusión sobre cuáles son las alternativas a lo que estoy hablando ahora para que ustedes puedan ir explorando todavía más allá el despliegue de sus modelos de Machine Learning, ¿no? Y bueno, vamos a ir con la primera parte, justamente que habla sobre TensorFlow y el despliegue de los modelos, ¿no? Entonces, TensorFlow, como ustedes ya saben, es un framework para aplicaciones de Deep Learning que incluye una infraestructura completa para la definición del modelo, el preprocesamiento y la ingestión de datos, el entrenamiento distribuido. Podemos exportar nuestros modelos a distintos formatos y distintos targets, ¿no? Y también para hacer el despliegue en distintos tipos de escalas, ¿no? Entonces, TensorFlow nos ofrece herramientas y utilidades y librerías para poder realizar todos estos pasos. Pero vamos a hablar específicamente de cómo desplegar un modelo de TensorFlow, ¿no? Imagínense que ustedes ya han logrado entrenar un modelo y han logrado probar el modelo en su máquina de hacer una aplicación. La verdad es que puede ser cualquier aplicación. Pero ¿cómo es que yo despliego esto a algún lugar en alguna forma en la que los usuarios van a poder ser capaces de interactuar con este modelo. Sin tener que pasarle mi código, tener que decirle que se instale las dependencias y ese tipo de cosas, ¿no? Porque eso es lo más complicado. Lo más complicado es que alguien ajeno a nuestra área o ajeno a nuestro trabajo pueda usar y probar y darnos feedback de cómo se está desempeñando el modelo. Entonces hay muchas alternativas y una de ellas es TensorFlow.js, que es bastante popular y es también una alternativa bastante buena que permite que ustedes corran un modelo de TensorFlow en el navegador usando JavaScript, ¿sí? Entonces solo tienen que convertir su modelo al formato correcto para que ustedes lo puedan leer desde JavaScript y ejecutarlo, ¿no? Realizar la inferencia desde JavaScript. El problema con esto es que existen algunos casos de uso en los cuales correr este modelo en el cliente no es adecuado. Por ejemplo, cuando el modelo es bastante pesado, ¿sí? El modelo es bastante pesado y tarda mucho en ejecutarse. Puede que nuestros clientes, como tienen distintos tipos de máquinas y distintos tipos de hardware, el rendimiento deje bastante que desear, ¿no? Entonces, la experiencia del usuario va a ser pobre si es que el modelo es pesado y el hardware con el que ellos cuentan no es adecuado. Otra situación en la que puede no ser adecuado correr modelos desde el navegador puede ser que su modelo sea muy grande en tamaño en bytes, ¿no? Y cada vez que ingresen a su página o a su aplicación tengan que descargar ese modelo, ¿no? Entonces, el uso de datos se va a incrementar mucho y puede que eso igual empobrezca la experiencia de su usuario, ¿no? Entonces, a veces en ese tipo de situaciones y en otras, necesitamos construir una interfaz más personalizada sobre la cual nosotros tengamos el control absoluto de cómo se va a ejecutar, cuándo se va a ejecutar, dónde se va a ejecutar, para que la experiencia del usuario sea más uniforme, ¿sí? Que no interese qué tan poderoso es su hardware, qué tan rápida es su conexión a Internet, simplemente que ellos puedan enviar una información, nosotros podamos agarrar la información, correr nuestro modelo y hacer una inferencia o hacer una predicción y mostrar esta predicción al usuario o devolver esta predicción al usuario. Entonces, es en ese sentido en el que nosotros vamos a trabajar justamente, asumiendo que ya tenemos un modelo de TensorFlow entrenado, ¿no? Solo para una forma de recordar, vamos a ver que hay una forma de poder entrenar modelos en TensorFlow que es usando la API de alto nivel con tf.keras. tf.keras nos permite definir modelos de Deep Learning usando redes neuronales en general en 3 simples pasos, ¿no? Primero, definir un modelo usando esta clase sequential que define una red neuronal como una seguidilla de capas que va avanzando una detrás de la otra. Entonces, con el modelo sequential podemos armar una red neuronal y con el método compile nosotros ya compilamos este modelo definiendo sus métricas, definiendo la función de costo y otro tipo de parámetros, ¿no? Y una vez que queremos entrenar, le podemos pasar los datos o un generador o alguna forma de generar los datos al método fit. Y este método lo que va a hacer es entrenar el modelo, ¿sí? Utilizando el hardware disponible, ya sea utilizando la CPU, la GPU o si ustedes tienen acceso a una máquina virtual con TPUs en la nube, ¿no? El modelo sequential, como les decía, es como una pila de capas, o sea, es una tras de la otra. Y se puede crear este modelo sequential pasando una lista de instancias de las capas al constructor. O sea, lo único que tenemos que hacer nosotros es pasarle capa tras capa tras capa que queremos incluir en nuestro modelo. Entonces, aquí pueden ver un ejemplo muy sencillo de cómo podemos definir un modelo. En este caso, estamos definiendo un modelo que tiene 2 tipos de capas. Tiene una capa que es la dense, que es una capa densamente conectada de neuronas, y una capa activation que simplemente define el tipo de función de activación que yo quiero aplicar a la salida de la capa densamente conectada. Entonces, para definir un modelo en Keras, en TF-Keras, en TensorFlow, lo único que tengo que hacer es al constructor del modelo sequential pasarle de forma ordenada las capas, ¿no? A medida que vayamos agregándolas. Entonces, aquí tenemos la primera capa que es una capa densamente conectada de 32 unidades. Y esta tiene 784, es la dimensión de la entrada, ¿no? Entonces tenemos 784 entradas y son 32 unidades las que van a ser las que se va a añadir, una capa con 32 unidades. Luego a esta capa le añadimos una función de activación de tipo ReLU Y después una capa extra más, que esta sería la capa de salida, que van a tener 10 neuronas. Y la función de activación va a ser una softmax, ¿no? Entonces, este es un ejemplo con el cual ustedes, por ejemplo, pueden entrenar una red neuronal para hacer la predicción sobre el típico modelo MNIST. Perfecto. Entonces, también pueden pasar las capas utilizando este método add, ¿no? O sea, hay varias formas sobre la cuales ustedes pueden construir un modelo de una red neuronal. Y en la parte de la compilación, como les decía, definen el algoritmo que van a usar para la optimización, definen la función de costo, ¿sí? Que en este caso puede ser, por ejemplo, categorical cross entropy, y algunas métricas para ir monitoreando durante el entrenamiento, ¿sí? Y a la hora del entrenamiento, lo único que nosotros tenemos que definir es dónde nuestro modelo puede encontrar el conjunto de entrenamiento, en este caso los datos de entrenamiento, las entradas y las salidas, y la cantidad de épocas o iteraciones que queremos que este entrenamiento se corra, ¿no? Y bueno, la última parte de esto es justamente la inferencia, ¿no? La inferencia, que es ya utilizar nuestro modelo entrenado para poder realizar predicciones sobre ejemplos o datos que nunca ha visto el modelo anteriormente. Y eso se realiza con el método predict, donde yo le paso uno o varios ejemplos, ¿sí? Sobre los cuales yo quiero realizar predicciones. Y esta es la forma en la que nosotros podemos hacer todo el flujo desde el inicio de la definición del modelo, la construcción, el entrenamiento y la predicción, ¿sí? Hasta ahí hemos visto bastantes tutoriales, hay mucho material en internet y hay un montón de información, ¿no? Entonces, lo que voy a hacer ahora es les voy a dar un pequeño vistazo de un notebook que he preparado, que ustedes lo van a tener disponible, que les voy a pasar el link de un repositorio donde tiene todo este código, donde van a poder ver justamente este proceso, ¿no? Entonces, acá tengo un servidor de Jupyter iniciado. Este es el repositorio que ustedes van a poder acceder. Entonces, en la carpeta de notebooks, yo tengo una carpeta que se llama Docs Transfer Learning, que es justamente el notebook con el cual yo estoy realizando todo este proceso. El ejemplo que vamos a utilizar es un ejemplo bastante bonito, que es una red neuronal que es capaz de clasificar imágenes, ¿sí? Y clasificarlas de acuerdo a las razas de perro con la que corresponde la imagen, ¿no? Entonces, vamos a pasarle una imagen o una foto de un perrito, y esta red neuronal nos va a predecir o nos va a clasificar esa imagen, nos va a decir a qué raza pertenece, ¿sí? Todo el dataset y también el modelo que estamos usando para entrenar está disponible en TensorFlow, ¿sí? En la librería. Entonces no tienen que descargar nada extra. Estamos utilizando TensorFlow, obviamente. Estamos utilizando la versión 2.3 para arriba, ¿sí? Y TensorFlow Datasets, que es otra librería en la cual organizamos, ¿no? Hay varios datasets organizados y preparados para que ustedes simplemente los usen. Entonces, el dataset que estamos utilizando se llama Stanford Dogs, que es un dataset con más de 70,000 imágenes de razas de perro, que tiene 120 razas de perros distintas, ¿no? Entonces, son 120 distintas razas de perro sobre las cuales vamos a hacer la clasificación. Entonces, este notebook es algo bastante común que ustedes van a encontrar en cualquier tutorial. De hecho, todo este notebook está basado en un ejemplo que lo pueden encontrar en la documentación de Keras. Entonces, ustedes se van a la documentación de Keras y van a los ejemplos de código, van a encontrar este notebook, obviamente con más detalle y sin algunas modificaciones que yo le hice, pero es básicamente en principio ese notebook, ¿no? Entonces, yo estoy utilizando este notebook. Como pueden ver, lo primero que hago es importar el dataset, definir algunas capas de preprocesamiento, como por ejemplo hacer un one-hot encoding para que a la salida tenga 120 neuronas y pueda extraer la predicción de una de ellas. Definir una capa de aumentación de datos, porque en visión artificial, cuando trabajamos con redes neuronales y tareas de visión, es bastante útil poder aplicar funciones de aumentación de datos para poder incrementar la capacidad de generalización de nuestra red. Entonces, aquí simplemente estamos generando, por ejemplo, rotaciones aleatorias, traslaciones o desplazamientos aleatorios, un random flip, ¿no? Que la imagen simplemente se va a espejar, y un random contrast, que simplemente va a incrementar el contraste de la imagen en un factor, ¿sí? Entonces, estas transformaciones estamos utilizando para que nuestro dataset incremente, digamos, en variedad y nuestra red neuronal pueda generalizar mejor con imágenes que nunca ha visto. Y lo que vamos a hacer acá, en vez de construir nuestra red neuronal desde cero, vamos a usar un modelo que ya ha sido probado y que está incluido en la librería de TensorFlow, que es la red neuronal de EfficientNet, ¿no? EfficientNet es una alternativa de red neuronal, de modelo, ¿sí? Por ejemplo, es una alternativa a MobileNet o tal vez ResNet, que tiene la característica de ser bastante eficiente, es decir, bastante pequeña y eficiente computacionalmente. Y lo bueno es que TensorFlow incluye este modelo, o sea, la definición de este modelo, la arquitectura, ya con pesos entrenados en el dataset de ImageNet, ¿no? Entonces ya tenemos un modelo de EfficientNet entrenado sobre ImageNet, que como ustedes saben tiene como 14 millones de imágenes. Entonces ya es un modelo bastante robusto y lo que vamos a hacer es aprovechar el concepto de transfer learning, ¿no? Entonces vamos a usar un modelo que ya ha sido entrenado, vamos a cortarle las últimas capas y solo vamos a entrenar las últimas capas para nuestra tarea específica. Entonces es lo que hacemos acá. Congelamos los pesos del modelo que ha sido entrenado sobre ImageNet y reconstruimos la última capa para añadir simplemente una capa densamente conectada, ¿sí? Una densamente conectada con la dimensión del número de clases que tenemos. Esa es la última capa, ¿no? Donde va a ser la clasificación. Luego compilamos este modelo con un optimizador de tipo Adam y con la función de pérdida del categorical cross entropy, porque es una función de clasificación, ¿no? Y eso es todo. Entonces eso, construimos el modelo y luego entrenamos el modelo, ¿no? Entonces acá he definido unos cuantos callbacks para poder almacenar o para poder salvar el mejor modelo en función del error de validación. Y esto lo que va a hacer es entrenar nuestro modelo y va a almacenar el modelo que mejor error de validación tenga, o sea, que más pequeño error de validación tenga. Y también he definido un callback para hacer un early stopping, ¿no? Cosa de que si nuestro error de validación no mejora durante 12 épocas, simplemente va a terminar el entrenamiento, ¿no? Esto es para ahorrarnos un poco de tiempo. Entonces pueden ver acá que ya he corrido este modelo, obviamente. Se ha realizado todo el entrenamiento y al final simplemente he ploteado un pequeño gráfico que tiene las curvas de aprendizaje, ¿no? Entonces pueden ver que en el caso de la validación tenemos esta curva y estamos almacenando solo el que tiene mejor precisión, ¿no? Mejor error de validación. Luego de eso también hemos añadido un paso extra que es, primero entrenamos la última capa, ¿sí? Y luego descongelamos las capas y volvemos a entrenar para poder extraerle un poquito más de precisión al modelo, ¿sí? Entonces es lo que estoy haciendo acá. Primero le hago el unfreeze, es decir, descongelo las capas y las vuelvo entrenables. Luego defino otros callbacks para poder guardar ese modelo y vuelvo a entrenar con el model.fit, ¿sí? Entonces, de esa forma, ustedes van a tener ya un modelo un poquito más preciso. Lo que voy a hacer acá es correr la prueba para que ustedes puedan ver que este modelo está funcionando, ¿sí? Y una vez que he entrenado ya la última parte, podemos probar el modelo, que es hacer la predicción. Esto es bastante sencillo, ¿no? Yo voy a definir un archivo de texto que ustedes pueden ver acá, que es el breeds.txt, donde simplemente tengo una lista de todas las razas sobre las cuales yo puedo hacer predicciones, ¿no? Esto es para convertir el número en un texto que corresponde a la raza. Y también tengo una variable guardada, el nombre del modelo que yo quiero utilizar para probar. Entonces, en este caso, el archivo de texto de la raza se llama breeds.txt y el modelo es el best local refined, que es el último que he entrenado. El tamaño de la imagen que acepta este modelo es de 224 por 224 píxeles. Y lo que voy a hacer es predecir el top 5, ¿no? De los perritos. Si yo le meto una imagen, me va a dar las 5 razas con mayor probabilidad. Entonces, lo primero que hago es cargar el modelo, ¿sí? Cargo el modelo con esta función que es keras models load model. Simplemente le paso el nombre del archivo y mi modelo ya ha sido cargado en la memoria RAM. Ahora ya puedo hacer inferencias sobre este modelo. Entonces, lo que estoy haciendo acá es estoy pasándole esta imagen como archivo para hacer la inferencia que se llama chihuahua.jpeg. Entonces, si vemos esta imagen, está acá. Es una foto de un perrito chihuahua, ¿no? Entonces, vamos a ver si clasifica este perrito de forma correcta. Aquí simplemente estoy hallando la predicción con el método predict, como ya les había mostrado anteriormente, y luego haciendo algunas operaciones para mostrarlo de forma más gráfica, ¿no? Entonces, hace la predicción y lo que obtenemos es Necesitamos importar, si no me equivoco, el matplotlib. Ya. Y lo que vamos a ver acá es una pequeña gráfica, ¿sí? De la foto y el perrito y las predicciones, las 5 primeras predicciones. Se pueden ver que Chihuahua tiene un valor muy cercano a 0. Eso quiere decir que la red está bastante confiada en que esto es un Chihuahua. Y bueno, entonces eso es lo que usualmente hacemos, ¿no? Hasta aquí todo está bonito, pero ¿cómo podemos ya desplegar este modelo en algo un poquito más utilizable? Muy bien. El siguiente paso es poder encapsular este modelo que acabamos de entrenar en un servicio web, ¿sí? Y lo vamos a hacer usando esta librería que se llama FastAPI. Entonces, FastAPI es un framework web bastante ligero de Python, ¿no? En Python, que permite crear servicios web de manera muy sencilla. Y tiene 3 características que son las que más llaman la atención de este framework, ¿no? El primero es que nos ofrece validación de datos de forma automática, ¿sí? Usando modelos de Pydantic. Entonces, nosotros vamos a crear modelos de datos usando básicamente clases de Python, ¿sí? Y de esa forma vamos a poder validar la información que llega a nuestro servicio web, que se hace de forma totalmente automática, eso es lo mejor. También vamos a tener esto que es extremadamente útil, que es la generación automática de documentación con Swagger. Entonces, una vez que ustedes definan su API y sus rutas, la documentación y una pequeña página de pruebas se va a generar de forma automática. Y otra característica de FastAPI es que, como su nombre lo indica, es bastante eficiente y rápido en comparación con otros frameworks, como por ejemplo Django o Flask. Aquí hay un ejemplo de una API en FastAPI en un solo archivo, ¿no? Pueden ver que es bastante sencillo. Simplemente necesitamos importar esta clase FastAPI, instanciar esta clase y luego añadir las rutas, ¿no? Entonces, esta notación se parece mucho a lo que hacemos con Flask u otros frameworks en Python. Entonces, simplemente con un decorador definimos qué tipo de request vamos a recibir en esta ruta. En este caso es un request de tipo get. Y en una función realizamos todas las operaciones que queremos cuando alguien haga una consulta o una solicitud a ese endpoint, ¿no? A esa ruta. Entonces, al final vamos a tener esta arquitectura para nuestra aplicación, en la cual tenemos los datos, que es nuestro dataset de los perritos. Realizamos el entrenamiento a través de nuestro notebook. Y luego, con nuestro modelo entrenado, ya podemos realizar la inferencia para que nuestro usuario sea capaz de interactuar con nuestro servicio, ¿no? Entonces, esa va a ser la arquitectura. Y la vamos a dividir en 2 partes, la parte del entrenamiento, que ya la hemos visto ahorita, y la parte de la inferencia, que la vamos a ver en un momento. Súper. Entonces, ahora les voy a mostrar de forma muy rápida el servicio que he creado con FastAPI, que también lo tienen en el repositorio, ¿no? Entonces, este es nuestro servicio, que yo tengo un pequeño esquema, que es el modelo que les mencionaba, que tiene ciertos datos, ¿no? Entonces tiene, por ejemplo, el nombre del archivo que ustedes han enviado, tiene el tipo del archivo, el valor de la predicción y el top de las predicciones, ¿no? Ustedes deciden cuántas predicciones quieren incluir. Entonces estoy instanciando esta aplicación. También estoy instanciando esta clase predictor, que es simplemente una clase que yo he creado para envolver la parte de la predicción del modelo. Aquí pueden ver que primero cargo el modelo, ¿sí? Load model. Y con ese modelo, cuando quiero hacer una predicción, simplemente ejecuto el predict. Solo estoy usando eso de mi modelo de TensorFlow, ¿no? El load model y el predict. Súper. Entonces, esta clase es la que va a realizar las predicciones. Y aquí tengo 2 rutas, ¿no? Tengo la raíz, que simplemente me devuelve en una cadena de texto, me devuelve el summary de mi modelo, o sea, toda la arquitectura de la red. Y esta es la más importante, que es la ruta predict, ¿no? Que tiene este tipo de response model, o sea, me va a devolver un modelo de este tipo, de esta clase. Y lo que hace es simplemente predice, ¿no? Predice el archivo que nosotros le mandamos a nuestro servicio. Y nos devuelve la predicción. Entonces lo podemos probar esto usando Ubicorn, que es un servidor asíncrono. Y ya van a poder verlo esto corriendo en su computadora, ¿no? Entonces ahorita más adelante les voy a mostrar cómo funciona esto exactamente. Pero de esta forma ustedes lo prueban de forma local. Ahora vámonos al siguiente paso, que es encapsular esta aplicación en algo que ustedes puedan compartirlo o ejecutarlo en un servidor en la nube. Y para eso vamos a utilizar contenedores de Docker, ¿no? Y Docker, para los que no saben, es básicamente una suite de herramientas que nos permite definir, crear y administrar contenedores para distintos tipos de tareas, ¿no? Podemos encapsular nuestra aplicación en un contenedor con todas las dependencias y las herramientas necesarias. Entonces, en nuestro contenedor yo voy a instalar TensorFlow, voy a instalar FastAPI y todo lo que yo necesito para correr mi servicio, ¿sí? Y lo mejor de todo es que estos contenedores son similares a una máquina virtual, pero mucho más ligeros, ¿no? Porque su funcionamiento es distinto a una máquina virtual, ¿no? Se basan sobre el kernel del sistema operativo y trabajan sobre eso en un entorno aislado. Entonces, yo puedo agarrar este contenedor o la imagen del contenedor y desplegar esta imagen en cualquier plataforma, ya sea Mac, Linux o Windows, o en servicios en la nube, ¿no? En máquinas virtuales en la nube. Y eso es lo que yo quiero hacer justamente. El Docker, para usar Docker, nosotros vamos a definir un archivo que se llama el Dockerfile. El Dockerfile simplemente nos define qué es lo que contiene nuestro contenedor o nuestra imagen del contenedor. Entonces, aquí usualmente tenemos siempre una imagen base, que es sobre qué imagen queremos trabajar. En este caso es Python 3.6 Slim, ¿no? Que es una versión muy reducida de Python. O sea, ya tiene todo Linux, un Linux incorporado con Python instalado, pero es bastante ligero. Luego de eso también definimos parámetros o variables de entorno, en este caso el puerto, puede ser el puerto. Y luego algunos comandos que queremos ejecutar como dependencias para que nuestro servicio pueda correr. En este caso pueden ver que solo estoy instalando las dependencias a través del requirements.txt. Y al final, un comando que va a servir para que se ejecute nuestro servicio. Entonces, ese es el Dockerfile. Es muy sencillo. Y acá lo pueden ver también, lo tienen en el repositorio. Y si ustedes quieren correr este contenedor Docker, pueden hacerlo usando Docker Compose, que también tiene ya tiene una herramienta, entonces pueden correr esto, y esto ya está corriendo dentro de un contenedor de Docker, ¿no? Ya no está corriendo directamente en su sistema operativo, sino está corriendo dentro de un contenedor de Docker, y pueden ver esto acá, sus servicios, ¿no? Que está corriendo el contenedor de Docker. Y ahora el último paso es cómo yo llevo este contenedor de Docker a la nube, para que cualquier persona en Internet pueda accederlo, ¿no? O tal vez la gente que yo quiero que acceda. Entonces, vamos a utilizar un concepto muy interesante que es el concepto de serverless computing, ¿sí? Serverless computing es un modelo de ejecución que se está volviendo bastante popular, bueno, ya es bastante popular desde hace algunos años. Es un modelo de ejecución en la nube que aprovechan proveedores de la nube, en el cual la característica principal es que todos los recursos, ¿sí? Estamos hablando de todos los recursos de cómputo, almacenamiento, memoria, todos es configurado e instanciado de forma automática y sobre demanda, ¿no? A medida que ustedes lo necesiten. La importancia de esto es que todo ese trabajo de aprovisionamiento, de configurar una máquina virtual, de configurar un clúster, de configurar los puertos, el balanceo de carga, todo ese tipo de situaciones se delega al proveedor de la nube. Obviamente se paga por esto, ¿no? O sea, tiene sus tarifas que son usualmente más elevadas que configurar tu propia máquina virtual, por ejemplo, pero en ciertos casos es mucho más conveniente, ¿no? Lo mejor de esto es que nos tenemos que preocupar solamente en el código fuente y ya no en los detalles de configuración, de provisionamiento y de ese tipo de cosas. Los tres principales proveedores de la nube tienen sus opciones serverless, así que ustedes pueden aprovechar cualquiera de ellas, ¿no? Pero vamos a utilizar una en específico que se llama Google Cloud Run, ¿no? Google Cloud Run es un servicio de Google Cloud Platform que nos permite instanciar contenedores Docker de forma serverless, ¿sí? Lo único que necesita Google Cloud Run es el Dockerfile, ¿sí? Bueno, en este caso, una imagen de Docker, ¿sí? Y nosotros podemos pasarle esa imagen de Docker a través de un repositorio con el Dockerfile. Lo mejor de todo es que Google Cloud Run nos permite escalar a 0 contenedores. Es decir, que si nadie está utilizando la aplicación, no se nos va a cobrar nada, ¿no? El flujo de desarrollo es bastante ligero. Les voy a mostrar aquí. Van a ver que en menos de 5 minutos vamos a tener nuestro servicio corriendo. Y también nos ofrece facilidades para integración continua y despliegue continuo, ¿no? que es bastante útil, en especial si ustedes tienen un equipo pequeño de desarrolladores y no quieren contratar o no tienen la posibilidad de contratar gente especializada en la nube, ¿no? Perfecto, entonces, ¿qué necesitamos para poder desplegar? Lo que ya les he mostrado, ¿no? Docker Compose es opcional, Python obviamente y una cuenta de Google Cloud, ¿no? Aquí es una nota bastante importante. Para que ustedes puedan utilizar lo que les voy a mostrar ahora, necesitan una cuenta de Google Cloud activada con su tarjeta de crédito. Pero no se preocupen, no les va a cobrar nada. O sea, todos los servicios que vamos a usar son básicamente gratuitos, ¿sí? Google Cloud tiene una capa gratuita en donde ustedes les permite tener hasta 2 millones de requests, creo, y un cierto tiempo por mes de forma gratuita. Y para experimentos básicos como este, da más que sobrado. O sea, que no van a tener que pagar nada, pero sí van a necesitar una tarjeta de débito o crédito para poder activar su cuenta de Google Cloud. Entonces, al final, nuestra arquitectura va a terminar así, ¿no? Ya con más iconos. Tenemos Jupyter para la parte del entrenamiento, en la parte de las pruebas, en un notebook. Y tenemos Docker en Google Cloud Run para nuestro servicio API REST, ¿sí? Y ahora les voy a mostrar esa parte, ¿no? Entonces, voy a ir a mi consola de Google. ¿Sí? Pueden ver acá, es la consola de Google Cloud. Y lo que voy a hacer es ir al servicio de Google Cloud Run, e iniciar un servicio, o crear un servicio. Y este servicio, como pueden ver acá, tenemos que definir varios parámetros. La región lo pueden dejar por defecto. El nombre del servicio le voy a poner docs TensorFlow, digamos. Luego, ustedes pueden desplegar este servicio en base a una imagen de Docker que ya está construida, o pueden construir la imagen en base a un repositorio de código fuente en GitHub. Entonces, yo voy a hacer justamente eso. Como ya tengo esto en un repositorio de GitHub, voy a configurar el despliegue desde ese repositorio. Entonces, es muy sencillo hacer esto. Ustedes tienen que conectar su cuenta de GitHub con Google Cloud y elegir el repositorio. En este caso, mi repositorio se llama TensorFlow Docs, Fast API. Y aquí tienen que definir cómo quieren desplegar su servicio en base al repositorio. Entonces, yo voy a definir un branch, que en este caso va a ser el branch master, sobre el cual va a escuchar este servicio de Cloud Build, que es otro servicio para hacer integración continua y despliegue continuo. Y va a escuchar cambios en este branch. Y el tipo de construcción, o sea, el tipo de build para que se despliegue este servicio va a ser el Dockerfile. Entonces, lo que va a hacer Cloud Build va a ser dentro de mi repositorio, va a buscar el Dockerfile que les mostré hace un rato. Y en base a este Dockerfile va a construir una imagen y la va a desplegar en Cloud Run. Entonces, todo esto se hace de forma automática y en pasos muy sencillos, ¿no? Aparte de esto, voy a necesitar agregar un poquito más algunas opciones avanzadas acá, como por ejemplo, la capacidad. Aquí, como estamos corriendo TensorFlow, entonces necesitamos un poquito más de memoria. 512 megabytes es suficiente. Y la CPU no interesa, esto es igual suficiente. Y lo mejor de esto es esto, ¿no? El auto-scaling, ¿no? Esto es el escalamiento automático que Google Cloud va a ejecutar si es que su servicio o si es que su aplicación tiene muchos usuarios o tiene muchas solicitudes, simplemente va a empezar a instanciar más contenedores. Entonces, ustedes pueden definir un mínimo que es 0. Cuando es 0, simplemente no les cobra nada porque nada está corriendo. Y un máximo, en este caso le puedo poner 1, que es suficiente para esta prueba, ¿no? Y una vez que ya tienen configurados esos parámetros, simplemente le voy a dar que voy a permitir invocaciones no autenticadas, es decir, va a estar abierto y público en la nube. Tengan mucho cuidado con esto porque si alguien encuentra, digamos, su endpoint, puede empezar a lanzarles requests sin parar y pueden incrementar su factura. Pero si es para pruebas, obviamente esto va a durar, digamos, un cachito, unos cuantos minutos, entonces no pasa nada. Y listo, cuando le doy el create, ¿sí? Esto se empieza a crear. Y todo lo que han visto funcionando de forma local se va a empezar a desplegar en la nube. Entonces, creo que ahora, esta es, veamos, la última parte de la charla. Sería bueno para hacer preguntas mientras esto se va desplegando, que va a tardar unos 2 minutos.
Súper. Más bien tenemos un par de comentarios. Está Denis que dice, muy buena charla, bastante completo y saludos.
Gracias, Denis. Bueno, entonces pueden ver que esto se está desplegando. Cuando ustedes crean por primera vez el servicio, se crea un contenedor como un placeholder, que es simplemente un hola mundo. Si hacen clic acá, tienen O sea, ya tienen un servicio corriendo, pero es simplemente algo de como que usa un placeholder nada más, ¿no? Pueden ver ustedes, pueden monitorear el despliegue yendo a la interfaz de Cloud Build. Y acá en el historial pueden ver el último build, que es este, ¿sí? En el cual ven todos los pasos que ya se han configurado de forma automática para desplegar su servicio. Entonces tiene, por ejemplo, el paso de build primero, donde construye la imagen de Docker. Luego el push, donde sube la imagen de Docker a la nube para que tu Cloud Run pueda acceder a esa imagen. Y luego el último paso, que es el deploy. Ahorita sigue siendo el push, si no me equivoco. ¿Sí? Y el deploy, que simplemente agarra esa imagen que le hemos subido a la nube y la despliega en nuestro servicio de Cloud Run. Entonces, sí, esto va a tomar un minuto más o menos. Pero al final ya vamos a tener nuestro servicio de Fast API corriendo en la nube, ¿no? Sin necesidad de instanciar máquinas virtuales, sin necesidad de instalar dependencias en una máquina de Linux o tareas como esas, ¿no? Entonces pueden ver que ya estamos en la etapa de deploy, ¿sí? Entonces, lo mejor de todo esto es que ustedes también tienen acceso a todos estos logs, así que si algo pasa, si algo anda mal, digamos, van a poder ver los errores, ¿no? Van a poder ver los errores, monitorear qué está pasando, tal vez hay algún error en su Dockerfile, ¿cómo se dice esto? Corregirlo y de forma totalmente automática, una vez que ustedes hagan push a su repositorio en GitHub, esto se va a volver a correr y se va a volver a desplegar, ¿sí? Sin necesidad de que ustedes tengan que copiarse el zip, pasarlo por FTP al servidor, compilar y hacer algo de ese tipo, ¿no? Entonces, esta es la idea detrás de este servicio de Cloud Run, ¿no? Esta es la idea detrás del concepto de serverless, que ustedes dejen de preocuparse por la configuración y la administración de sus servidores. Serverless no quiere decir que no existen servidores, simplemente que toda la configuración, el aprovisionamiento y el manejo se va a realizar por el proveedor, ¿no? O por, en este caso, el servicio que ofrece el proveedor. Muy bien, entonces vamos a ir a nuestro Cloud Run para ver cómo se está desplegando. Pueden ver que aquí se está actualizando.
Disculpa, José. Aprovechando
¿Sí?
que se está actualizando, tenemos una pregunta también.
Claro.
Que nos dice Fernando. José, me llamó mucho la atención sobre el uso de Fast API y lo de Docker también. Una pregunta. ¿Cómo fue tu experiencia en la certificación de TensorFlow y a quién recomendaría certificarse?
Ya, perfecto. Esa es una buena pregunta. Sí, Fast API es una librería bastante interesante. Les recomiendo que le den una mirada y es muy, muy fácil de usar, ¿no? En cuestión de la certificación, la verdad es que yo estaba estudiando, digamos, esto de TensorFlow hace bastante tiempo y me llamó la atención el año pasado cuando lanzaron este programa del Developer Certificate, ¿no? Me fui a la página, empecé a averiguar qué se necesitaba y vi que existía bastante material y muchos de los conceptos que se necesitan son conceptos muy, ¿cómo se pueden decir? Generales, ¿no? Generales del despliegue en TensorFlow. Yo recomendaría que tomen, o bueno, que intenten sacar esta certificación si es que les interesa más hacer este tipo de cosas, ¿no? Ya llevar, saltar del ejemplo que les mostré del notebook a alguna aplicación en específico y poder encapsular este tipo de comportamiento o red neuronal en cosas más útiles, ¿no? Entonces, si les interesa hacer ese tipo de cosas, hay bastante material en la página de la certificación. Incluso hay un curso que ustedes pueden acceder, ¿no? Donde van a aprender bastantes temas relacionados con no solo visión artificial, sino también procesamiento de lenguaje y este tipo de cosas. Entonces, si les interesa aplicar TensorFlow ya a cosas un poquito más reales, entonces sí, la certificación vale la pena, ¿no? Bueno, entonces ya he terminado de actualizar el contenedor, bueno, el servicio. Entonces, pueden ver que acá en Revisions tenemos todas las versiones de contenedores que hemos desplegado. Y en URL está la URL de nuestro servicio ya corriendo en la nube. De hecho, ustedes podrían ahorita acceder a esta URL. Entonces, como les había mostrado anteriormente, en la raíz nos devuelve la arquitectura de la red. Pero lo que más me interesa a mí es hacer la predicción. ¿Sí? Es hacer la predicción. Y simplemente tenemos que ir a la ruta de docs, ¿no? Esta ruta de docs nos la ofrece Fast API. O sea, esto ya viene gratis, básicamente es regalado. donde nos define todas las rutas que hemos puesto en nuestro archivo. Aquí tienen el model summary. Entonces, tiene documentación aquí generada automáticamente. Yo puedo ejecutar este request y ver el resultado. Y en Predict, lo más genial es que cuando yo defino el tipo de datos que quiero recibir, la documentación se genera de forma automática. Entonces, aquí me dice tranquilamente, me dice, el body del request necesita un file, ¿sí? Entonces, si le doy el tried out, aquí ya me genera un botoncito para poder subir un archivo y voy a hacer justamente eso, ¿no? Voy a subir un archivo, en este caso el Chihuahua, para ver si sigue funcionando. Y cuando yo le dé al execute, ese request se va a mandar a mi servicio y se va a realizar la predicción. Y voy a obtener aquí la predicción. Como pueden ver, la predicción es Chihuahua y me da el top 3, ¿no?, de razas de perro a los cuales puede pertenecer esta imagen. Entonces, Chihuahua está con el 99% de certeza, básicamente. Y tenemos otros, ¿no? Mexican Hairless and French Bulldog. Voy a probar con otro archivo más que tengo aquí en el repo, que es de el pack, ¿no? Es un perrito pack, como el Frank de Hombres de Negro. Y pueden ver que también me hace la predicción, ¿no? En este caso es un pack, ¿sí? Y bueno, eso era todo lo que les quería mostrar. No sé si hay alguna otra pregunta, tal vez. Van a tener todo este material en el repositorio de GitHub. Lo pueden encontrar acá, ¿no? En estas diapositivas también, que le voy a pasar a Leigh para que les comparta. Y así ustedes van a poder probar por sí mismos todo lo que les he mostrado hoy, ¿no?
Súper, muchísimas gracias, querido José. Creo que ya hemos resuelto las dudas que estaban ahí por el chat en YouTube y acá también en el Zoom. Y pues otra vez muchísimas gracias por tu tiempo, por compartir algo tan interesante, algo que pues va a servir también a todas las personas a poder llevar su conocimiento a un otro nivel. Y otra vez estamos muy contentos de tenerte en este evento del TensorFlow Everywhere.
Gracias a ti, pues Leigh, encantado de compartir esto con la gente. Y bueno, atento a cualquier novedad.
Muchísimas gracias. Muchas gracias, José. Entonces, vamos continuando con la siguiente presentación. Ya lo habíamos anunciado, ella es Leigh Johnson. Es también Google Developer Expert en Machine Learning. Actualmente es ingeniera en Machine Learning en Slack. Y pues le gusta mucho todo el tema de el Age of Machine Learning. Nos va a contar un poco sobre lo que es MLOps at the Edge. Hello, Leigh. Good morning.
Hi, buenas tardes. Hello.
Hello.
I'm going to be giving this talk in English today. I'm sorry in advance. Puedo leer y escribir más mejor de lo que puedo hablar. So tweet at me if you have any questions or if you just want to chat a little bit more about this. And let me go ahead and share my screen.
Sure. We're so happy to have you and thank you so much.
Thank you. Okay, can you see my screen?
Now, yes.
Okay, perfect. And how is the audio on my side? Can you hear me okay?
Yeah, we can hear you very well. Thank you.
Okay, perfect. So I'll tell you a little bit about my journey, about how I got here. Around 3 or 4 years ago, I set out on a mission to give my Raspberry Pis the gift of sight. These are really small, about $20 or $30 computers. They're about this big. And I found these to be amazing because this small computer that I'm holding in my hand is more powerful than the first computer that I ever had way back in the 90s. And my background is not necessarily in data science, but I found my way here. I have a background that makes generalist engineering look like an extreme sport. I've done database reliability engineering, which is like site reliability engineering, laser focused on the data tier. I've done infrastructure engineering, video games development, web development, which is how I found myself optimizing marketing pipelines, learning a little bit more about modeling churn, building Bayesian models eventually in order to create better marketing and advertising offers. And that's led me here today, exploring computer vision. Okay, so the talk I'm going to be giving today is about detecting 3D print defects using computer vision And I'm going to be doing this at the edge on these really small devices. And this is a really deep technical deep dive covering a wide breadth of material. So I'm going to be flying through it. If you have any other questions or comments, please tweet at me, and you can find the slide deck online if you want to review this later and steal, copy anything. The code is all online, released 100% under AGPL. So everything you're seeing today is open source. And please feel free to use it for your own research or your own personal projects. Okay, so before I get started, I just want to tell you an alarming statistic that 87% of data science projects just never make it to production. And I found this extremely alarming as a production engineer myself. And I wanted to dig in and explore more about why that was and see if I could make this a little bit easier for myself, for my colleagues. So when I got exploring a little bit about what it takes to productionize a machine learning model, I found that about half of the folks that were trying to deploy machine learning models were in the pre-production phase. They were still trying to figure out how to go from a notebook model to machine learning model live in production, where they were getting feedback about it and understanding how it performed in the real world. And I've encountered just about every one of the challenges that were cited in this study. And the biggest ones were challenges in measuring and proving the business value of the AI/ML solution. Sometimes there's a kind of a lack of clear strategy or clarity in success metrics. You don't necessarily know how ML is performing in the real world unless you think very deliberately about that early on. There's also a lack of trust towards AI/ML decisions, especially outside of the data science community, can be perceived as like a silver bullet or magic. And I wanted to demystify a lot of these. So a little bit more about the current use of AI and ML. About 1/3 of AI/ML projects get applied to embedded systems or some kind of predictive maintenance or predictive failure. So when I set out to go build a monitoring system for 3D printers, which are a mechanical system, I knew that I was probably onto a common use case, and it would be important to talk about this work and show others kind of the path that I had forged for myself. So here's the case study about how to do MLOps at the edge. And I'm going to be talking about a service called Print Nanny. So Print Nanny uses computer vision to automatically detect and stop failures in 3D printers. It's a type of mechanical failure. And it's an example of an embedded system running a machine learning model at the edge with fully offline inference. So a little bit about 3D printers, just to get you kind of up to speed if you've never seen these before. They range from hobbyists here to really high-end industrial machines, and they use different processes for each. Oh, yeah, what was that?
I just wanted to see, are you using your slides? I think they are not being updated.
Oh, can you see my screen?
Now, yes. Now, yes, thank you so much.
But not now.
Now we can see the 3D printer types.
Oh, so have you missed, should I go back and do?
Yeah, maybe just a quick review what you were showing us.
Yeah, let's do, we'll start here. That's okay. We're doing it live. All right, so welcome to 3D printers, and you can see the three 3D printers now. Or no?
Yes, we see 3D printer types. How is it? Yes.
Okay, cool. Thank you. I'm not sure what happened there. Let me know if you don't see the next slide transition, okay? Just raise a flag. It could be that Zoom is disconnecting, or maybe screen sharing is not live.
Sure, thank you. And yeah, go ahead.
Oh, I actually see your screen sharing is paused. Is that something that one of us has to unpause? Oh.
Can you try changing next slide, please?
Do you see the slide changing?
Nope.
No, okay. Interesting, okay. Should I try, I'll rejoin Zoom, come off and on again? How does that sound?
Just let me see 1 minute. Is he already here? Yeah, maybe just trying to rejoin and again share screen.
Okay, thank you everybody for your patience. Apologies for the,
No, it's okay.
I'll be right back.
Welcome back, Leigh.
Thank you. All right, let's try this again. Thank you everybody for your patience.
Sure.
Let's share this desktop. Okay. And
Try changing slides, please.
all right, are we seeing
Oh, yes.
flipping back and forth? Okay, perfect.
Thank you.
Yeah, of course. Okay, I'm gonna pull up notes here. Okay. So let's talk a little bit more about the type of 3D printers. So they range from high end to low end, and you can see that certain types of 3D printers used a fused filament fabrication model that slowly deposits filament layer by layer, building up the print one layer at a time. And over on the right, there are high-end 3D printing processes that use a UV light to cure resin. And rather than building up the print layer by layer with fused deposits, they add a resin, cure it and harden it, and then add a little bit more. And the reliability between these types of processes, like any manufacturing processes, is all over the place. And the size and scale is different as well. So the lower end 3D printers that hobbyists might have can fit like a football on the print bed, while some of the higher end big industrial machines are larger than me or taller than me. So a little bit more about some of the problems that are here. Because fused filament or fused deposition modeling takes hot extruded plastic and tries to melt it to build a print up. It's extremely unreliable. Jobs take hours or days to complete, and at any point something can fail. And the molten material heats up to about the temperature of a pizza oven. So it's very dangerous to leave something like this in your home or in your garage or a warehouse if you're a small scale manufacturer for days on end, unattended. Someone has to be there to watch the print, which is problematic because it's very expensive and slow. So the first thing that I knew if I was going to build a monitoring system for these is that I can't necessarily rely on the internet being available. If something were to go wrong or an internet connection were not available, I would still need to be able to stop the 3D printer. I didn't want to end up in a situation like this where people can't vacuum or open their doors or use their doorbells because they didn't have access to the internet. So a little bit more about the system requirements. We're going to be running at the edge using a Raspberry Pi that I showed you all earlier. And everything on the cloud side is in GCP, where I'm going to be doing analytics, telemetry. I will be training the model, doing evaluation, validation, and collecting performance metrics so I can understand how the model is performing in the real world. So the type of problems that we're looking for with this system range from really small imperfections, which you can see here. There's bubbling and oozing in the print as it gets built up layer by layer, to variations caused by temperature. And this you can see as the temperature changes, the material behaves differently. And this can vary within a degree or two. The material might behave entirely differently. And the model needs to be able to catch and understand this behavior. And then some of the print defects look a bit like abstract art. People actually pose and stage and light their failed 3D prints as if they were art, and I absolutely love this. And then there can be full-on catastrophe. 3D printers can catch fire, and this is extremely dangerous. And we want to be able to prevent, catch, and early warn on things like this. So it's very important that this is a system that emphasizes reliability. Really quickly, I have a couple of options for how to build this model. And we can build something called a binary classifier, where we're going to teach the model to predict whether a print has failed or not failed, taking it in an image frame. And then there's a probability distribution that expresses the chance that the print has failed or not failed. And you can see that this is captured at any single point in time. So that's one option for building a model. And here's option number 2. You can detect the contents of the frame and then calculate a health score. So you're not making a statement about whether the print has failed or not. You're taking an image frame. You're using a multi-class feature extractor, which you can see in the right, rather than fail or not fail. There's what's inside of a print. And then you can implement a second algorithm that says, okay, I've detected more signs of health or more defects than health signs within a print. And then decide based on that output whether something has failed. So I'd love to take an audience poll right now. If you had to go do this, which would you implement? Would you choose door number 1, the binary classifier, or door number 2, where you're implementing a multi-class classifier and then using some kind of linear algebra in order to determine whether the cumulative health score is going down or increasing? So if you type into chat what your vote and opinions are, we can come back and talk about this later, because I think this is an interesting question, and the answers vary, and there are good justifications for one or the other. So to understand a little bit more about the implications and how to improve them, let's go through real quick binary classifier implications. We're asking the algorithm one really complex question, and we're saying, at any point in time, is the print failing? And there are so many determinants to this outcome, and it can be impacted by training data set bias. So if my training data set bias if my training data set happens to contain more failures that have blue filament, the model will tend to predict that failures occur in prints using blue filament. And that doesn't necessarily generalize well to the real world. Any skew in my training data set is expressed in the model's production performance to a pretty high degree. So that means acquiring or synthesizing a well-balanced data set is going to be the way to improve and perfect this approach, which is really hard. It's very, very difficult to acquire a well-balanced data set. So looking at the model ensemble, we're asking the algorithm a series of really, really simple questions. We're asking what things are in the image, where are those things? And then I can sum the confidence of how those things are detected and decide which of the detected things are a defect. And then this lets me create individual modeling strategies for each of the detected defects. So I can introduce new types of detected defects and not necessarily have to retrain the entire system end to end. Skew in my training data set also encodes a much simpler form of bias where maybe I can't detect a nozzle in a certain printer, Or maybe I can't detect a certain type of defect with a certain color filament, but that doesn't impact other detected defects. So this makes it a lot easier to improve and continuously study the model in production, even though it seems like it's a lot more complicated. Okay, so to understand some of the real world usage, who are the people using this? Small scale manufacturers are people that sell 3D prints on places like Etsy, Shopify, eBay. They do small batches, typically printing 1 or maybe even a dozen things at a time. And they're also hobbyists like me who just print things because they like to make robots or they like to experiment or make stuff. And there was a real opportunity here, I thought, to innovate because the pandemic disrupted global supply and people started to fill warehouses with small scale manufacturing tools. Because large scale manufacturing disrupted the ability to fulfill components, people started making them themselves in garages and small scale warehouses. And I think this is probably going to change the global economy forever. So talking about data product maturity, there are 3 main steps. We're going to go through and prototype the path first, which is how I developed and validated that this product would meet market demand and would actually perform to specification. And then step 2 is refining the results, making it better, adding additional value. And then 3, once we've added enough value where people are kind of like chomping at the heels in order to get this, we need to figure out how to scale to meet that customer demand. All right, so what is our minimum awesome product? What's the smallest thing that we could build in order to prove the concept, get people excited, get people signing up, and then develop a feedback system in order to improve results over time? And so here's what I came up with. We need to train an object detection model. We need to deploy it to an edge device. We need to calculate health score trends over time, and then automatically stop unhealthy prints, and then develop some kind of feedback mechanism just so people can say, yes, it did a good job. Nope, didn't do a good job. And so here are the components. I started with a pile of Raspberry Pis, Pi camera, Prusa i3 MK3S 3D printer, and an Inci Rambo, which is a really small embedded, it's a small Arduino-based device, which is used as the actual hardware controller for the printer. And then on the software side, I was lucky enough that some open source software already exists to control 3D printers called Octoprint. And I was able to develop my solution as a plugin to that software. And you can see it on the right. The broader software is provided by Octoprint. And I was able to just embed my machine learning model and provide a really simple interface. So very quick to prototype and get into production. Training data. This is the hardest part of any data science project. For the initial training, I scraped YouTube for videos that people had uploaded of time lapses of the 3D print. They're very soothing if you go and look them up. If you do this yourself, I use a tool called YouTube DL, but please pay attention to content licenses and make sure that if you're using things for commercial purposes like I am, that you attribute or respect the license accordingly. To label things, I use Microsoft's Visual Object Tracking tool. And this is a tool that you could install on your desktop and label bounding boxes by hand. The initial data set that I came up with was about 3,000 frames and about 9,000 objects, which sounds like a lot, but it only took a couple of hours to label. I ended up discarding half the data I collected. So if you're doing this yourself, know that you might have to throw away a lot of data. And the one thing that's really good about VOTT is it can export to a variety of formats. TF records are the ones that I ended up using, but also CSV and JSON, which is helpful for other projects. The baseline model that I developed, I did using something called AutoML Vision Edge. I knew that even though I can train an object detection model myself, it might take me a fair bit of time. And I might end up perfecting that model or tuning that model for weeks. And I wanted to get something in front of an audience very quickly. AutoML Vision Edge is perfect for this. I was able to upload my data set, train a model, and export the trained model in less than 24 hours, I would say. And I had a fully ready to productionize model. The steps were just after I labeled my data set, I uploaded the annotated data to Google Cloud Storage. I kicked off training with a certain set of parameters that I'll show you in a later slide. And then that's all I had to do. So I ended up using the best trade-off option just to see what it would do. The AutoML Vision Edge product is optimized for machine learning at the edge. So it uses a quantized input. So instead of taking a floating 32, like a floating point input, the model is quantized to an 8-bit integer instead. The model that I trained cost about $120 USD, which if you consider the cost of employing a data scientist or even myself taking time as a data scientist to go out and train a model, this is fairly inexpensive compared to all of those solutions. So this felt like the right decision to me from a business perspective. The tools to evaluate this model were all through the UI. So I used what's called intersection. The vision models use something called intersection over union in order to determine the accuracy of bounding boxes in addition to a classifier. So in a multi-class problem, the F1 score you can see displayed on the left right here. And precision and recall are an expression of the relationship in the confusion, the relationship between true positive, false positive in a confusion matrix. And I knew for this particular problem that a false positive score is something that I wasn't necessarily sensitive to. I had done some user testing earlier, and I knew that people didn't really mind getting false alarms, which is what a false positive would mean in this case. And if they had gotten a false alarm, they would just look at the print and say, "Ah, it's fine," and then discard it. So in that case, it means that I don't necessarily need to optimize for a very high precision score, which is what my model ended up doing. So this is an area that I noted for improvement later. One of the things that I liked about the AutoML system too is that you could take the metrics and load them into a collab notebook and go and explore them later. And I would later use these as a baseline when I started training my own model, just to see if I could improve over Google Cloud visions like AutoML grid search. You can export the TensorFlow graph from the saved model. And I'm going to fly through the next couple of slides, but please, if you want to replicate this work, just tweet at me. So this is a way that you can inspect any type of saved model. You can export the graph to a format that you can view in TensorBoard. TensorBoard is a UI for viewing metrics. And in the Graph Explorer, you can click through the architecture of the model and begin looking and seeing some of the choices that were selected for this AutoML model. And I use these as inspiration to go and build my own architecture. So I saw that some of the decisions that had been made in this model was that a separation convolution was used. This is a type of 2D convolution. So rather than one of the optimizations that this model made is typically a 3D convolution is used, and it's very expensive to perform on a small device. And then the separatable convolution was one of the key pieces of the architecture that made it outperform MobileNet in terms of speed and accuracy benchmarks. Unfortunately, I also noticed my data quality had suffered. So when I was analyzing my model in the AutoML UI, I could see that some of the false negatives were actually errors on my part. If you see on the right, these were labeled as false negatives where the nozzle was detected accurately, but not labeled accurately. So the classification fell into the false negative category. And I knew, all right, I've got to improve the quality of my data before I can do anything. Luckily, the AutoML model exports to TensorFlow.js. Oh, the visual object tracking tool that I use can import a TensorFlow.js model and can use that model as a guidance. So if you look on the right, this is me panning through a video, and the TensorFlow.js model is actually providing the bounding boxes. So now, instead of dragging bounding boxes manually, the model is guiding the choices, and I'm just augmenting them. This is a lot faster. It was about 10 times faster than doing manual annotation just on its own. Here's an example of breaking out confidence scores and health scores, and you can begin to see where, as defects are introduced to the print, if we were to think about these as a cumulative score, we could then express using like a polynomial curve where health is declining. So if we overlay all of these as absolute scores, it's really obvious, oh, this is where defects started occurring in the print. And then if you express it as a cumulative score, the downtrend is even more obvious here. There's a failure detected right there. The prototype was pretty straightforward architecture. The Raspberry Pi ran the model hooked up to a Pi camera with a serial-based control scheme for the 3D printer. And then the web application, which is just a sign-up form connected to a database, was deployed in Kubernetes and GCP, which is a bit like deploying into an empty room at that stage. Okay, so we have this entire end-to-end machine learning system, and it only took me about 4 weeks from the point where I had the idea, $130 for the machine learning part, $400 for the logo and domain. You know, those are very important, but just to give you a comparative cost, this is a very inexpensive way to prototype machine learning compared to hiring a data scientist or becoming an expert in computer vision. And even if you are already an expert, this was just a way to validate the idea very quickly. About another $30 in Cloud SQL, load balancer, compute engine. And that got me to about 2,000 beta signups where I'm really testing this product in front of real people. It's worldwide. And this is one of the things that I think is really cool about the small scale manufacturing trend that we're seeing. Everywhere supply lines were disrupted, and everywhere people are stepping in with these small 3D print shops in order to meet demand for parts that are no longer available. So now talking about how we improve this, if you go back to the intersection over union loss metric, you can see that in certain situations, prints are detected, and this is not wrong, but it's also not right. And I needed to provide a way to calibrate the area of interest where only things that were inside of that area would be included. And this is the same metric. This is the same algorithm that's used in order to calculate loss. Okay, continuous learning. How do we continually make it better and improve it? Well, publishing telemetry data is important. We need to process the data stream, retrain the model, run experiments with new models, deploy those, and then monitor the results. Simple stuff, okay? What are some things that we can use in order to support this? Well, Google Cloud IoT Core provides a fully managed service that supports MQTT, which is an IoT-based protocol that's very small and supports full duplex messaging. So in a duplex messaging stream, messages can go both ways. And then it also supports half duplex, which is HTTP. So messages can go one way. It's serverless, so there's nothing that I have to manage myself, which is quite nice if you're doing this as like a nights or weekends project. There's a cloud pub sub message relay, so you can hook it up to other services. And in my case, I used Apache Beam in order to subscribe to cloud pub sub messages. And then there are certain guarantees around the messages, which are ideal for IoT devices. So having a quality of service setting of 0 says at most once a message is received, or at least once a message is received. So The initial setup for the device involves a key exchange where from the cloud, I create and sign a key and then send it back to the Raspberry Pi. And then the Raspberry Pi uses that key to sign requests. And this form of identity management is important because each of these devices represents kind of an unsafe actor, if you think about it. I was trying to be very thoughtful about the way that I managed an internet-connected camera in someone's home. So it was really important to me to have very strong credentialing and very strong identity management in this process. So every Raspberry Pi receives its own certificate, totally throwaway. It's not the private key that the device receives. It's saved only on that device and just reprovisioned as needed. On the MQTT and PubSub side, each device can publish messages to a topic, and then those are relayed over to PubSub. I'm going to keep flying through this because I know we're kind of over time. Apache Beam is what I'm using in order to process these messages. And these are, Apache Beam is a great choice here because it has unified batch and streaming. So you can write the same code to do batch processing or the same code to process events in real time. There's also a windowing model to it. So if I want a window over a fixed interval or by a sliding window, Apache Beam provides interfaces and I don't have to implement those myself. Now it's time to train my own model. This is where I wanted to see if I could do better than the AutoML service provided by Google. I use the Object Detection API, which contains a zoo of models that you can use for fine tuning, along with an interchangeable backbone and some made up model architectures. So you can put these together and try to build your own architecture. I improved on the mobile net architecture with the 2D convolution that you all saw in an earlier slide. The model version framework was about 100 lines of Django code. And that's just what I used in order to version the model artifacts and ensure that the latest model was always deployed to the Raspberry Pis. The architecture is starting to get a little bit more complicated, as y'all can see. It's not just one thing in a Kubernetes pod anymore. One of the things that kept me sane through all of this was always treating infrastructure as code. I used Ansible configuration for servers and always Terraform for cloud. And my training rig looked a little bit like this. I didn't do cloud training at first. Since I had a GPU machine, what I did is I created a semi-automated pipeline to download all of the data that I'd saved to the cloud, train for about 24 hours, and then upload everything again. And this is starting to get into the type of reproducible factory model that is valuable when you're trying to do machine learning, when you're trying to operationalize machine learning. Quantized model performance is something that I need to study really closely. So quantization is when you reduce the signal range of any type of model. It's an old signal processing strategy. And in this case, I'd gone from float representation to 8-bit integer representation. And understanding the impact that that had on performance and latency was important. I used application traces to do that, which gives you the ability to look at heat maps of latency. Okay, so here's the final refined concept, totally done end to end, where we've got a Raspberry Pi running models at the edge. In Kubernetes, there's a Django web application that's serving requests, for example, signups or the ability to view your model or view the stream offline. The Apache Beam is running in a data flow worker. A pub subtopic is provides IoT events that you can subscribe to and sync to other locations. I've got a data lake in Google Cloud Storage. The MQTT bridge is the basis for all messages that flow through. And the GPU workstation represents offline training, which is done on a cron. And so this is kind of V1 of end-to-end MLOps. But it doesn't exactly scale. What happens when I need to train a model that's bigger than can fit on one GPU? And this is the case. This happened to me really quickly. I exceeded capacity of my training, and now I've got to work on distributed training. So everything that's on my GPU workstation, I've now got to port to a pipeline in the cloud. Luckily, Google Cloud makes this fairly easy. And the right mechanism to do that is to build a Docker image, as we saw in an earlier talk. So it's very straightforward to package your trainer code. And in my case, I'm going to be using a framework called TFX, TensorFlow Extended, in order to build reproducible machine learning pipelines. And so this is stage 3, getting into the full factory model of reproducible machine learning. The things that I'm most interested in from TFX are the transformer side, which lets me write the same transformations in training that are used for inference, the training code, obviously, and then the evaluator. The evaluator side is something that's going to let me explore the data validation metrics. So I'll be able to see if there's data drift over time. All right, thank you, everybody. I appreciate y'all coming to my talk. If you want to tweet at me, I'm at Leigh. And now I'll turn you all over to Leslie.
Thank you so much. What a great presentation. It's so exciting actually to see like the whole pipeline project. And we have some questions in the chat. Maybe you will help us answering there in order to move forward because we are just at the end of the event. But again, thank you so much. We'll be sharing a bit more about the slides and Leigh information on the YouTube channel and here. And yeah, one more question. One question is about the amount of work for each ID's potential state effects on early slides. Yeah, I think I will find more information on that one. And Fernando is also asking about the Apache stream, but maybe you can, in general, explain that before going to the last talk.
Yeah, I will post a little bit in chat so we can segue right to Joanna. I don't want to keep all. Okay, thank you.
Thank you. Thank you so much, Leigh. Great presentation.
Thank you.
So for closing this event, we are having also Joanna Carrasqueira. She is a Developer Relations Program Manager for TensorFlow at Google, and she's leading the outreach and engagement strategies for the global TensorFlow community. So thank you so much, Joanna, for being here, and thank you for joining us today.
Thank you so much, Leslie, for the invitation. It's my pleasure to be here today. Buenas tardes a todos. Muchas gracias por convidarme para el evento. Estoy muy emocionada por hablar de la comunidad de TensorFlow. Mi presentación va a ser en inglés porque mi español no es tan bueno. Así que voy a compartir mi screen. Okay. Let's see. Can you see my screen?
Yes, we can have it now.
Yeah. You see it now?
Thank you. Yeah, now we can see it. So welcome. And,
okay. Okay, thank you so much for the invitation to present about the TensorFlow community and how you can get involved. We've seen a lot of exciting growth in LATAM over the past couple of years. So thank you so much to people like Leslie who organize this kind of events. So we have the chance to talk a little bit more how you can get involved and the programs that we offer for you to join the TensorFlow community. So as you can see, our community is growing every day. And here's just a snapshot of the commits to TensorFlow since 2015 when we open sourced the technology. As you can see, we've already received 153,000 stars on GitHub, which tells us that you like our technology. And for that, thank you so much to everybody who uses TensorFlow, and thank you to the community. I'm always really impressed to see all your contributions and hard work, so thank you so much for that. TensorFlow is an open source framework, and our goal is to really enable our contributors by fostering an open and welcoming environment where all contributors with all levels of experience are welcome. Our diverse community is governed by the TensorFlow Code of Conduct, which is maintained by the project stewards, which are Thea Lumpkin and myself. And really our goal is to foster an open and welcoming environment, use inclusive language, be respectful of different viewpoints, and really focus on what is best for our community. Transparency is also a very important value in our community, and in order to keep transparent communication with everybody, all the design changes must be submitted through the RFC process. And I'm not sure if you are familiar, but the request for comments or RFC process is a great way to get feedback in large open source projects. Therefore, this is the primary way that we communicate our design rationale and receive feedback from the community. We adopted this way of engaging with the community when it comes to design changes, simply because it gives an opportunity to core and non-core contributors to propose an idea before we implement the change. So we've also started tweeting our RFCs, so please keep an eye on our Twitter account if you are interested in participating in one of the RFCs. And we manage this process on GitHub, and right now we have approved 84 RFCs, which is unbelievable given the fact that 30 RFCs were just approved in the last 6 months. So if you want to propose a design, we strongly encourage you to socialize your idea, recruit a sponsor, write an RFC, and respond to feedback and implement it on GitHub. Documentation is also the backbone of any open source project, and TensorFlow is no different in that regard. So far, we have 268 tutorials and notebooks that have been translated to 12 languages. Additionally, we have over 40 pull requests awaiting review. We really want to provide a good experience to our contributors, and in order to achieve this goal, we'll continue to support translation efforts into different languages. We do have that documentation in Spanish, and if this is something that you would like to participate and contribute to, it's a great way to start by getting involved in the community. So now let's have a more in-depth look at the different groups that form our community. In a nutshell, our vibrant community includes code and non-code contributors, community managers, and students. Currently, we have 167 ML and Leslie and Leigh, they are great examples of 2 GDs who are a part of our program. We have 80 TensorFlow user groups spread across the world. We have 13 special interest groups, more than 3,000 developers involved. We had so far 18 spotlight winners. We have more than 2,500 contributors, more than 9,000 commutes, and with this series of events, the TensorFlow Everywhere, we've hosted more than 28 events, and they have been translated into 9 different languages. So just to give you, just to share some of the impressive numbers that we have in our community so far. I'm just going to give you an overview on how you can get involved in TensorFlow through the TensorFlow user groups, machine learning GDs, and the special interest groups, because these are our primary groups to get started with. So right now we have 80 TensorFlow user groups in 35 countries, and these groups, they have reached more than 100,000 developers last year. They, as I mentioned, these groups are hosting the series of events that is called TensorFlow Everywhere, and they have been translated into 9 languages. Joining one of these groups is a great way to engage with the community, and that's exactly what we're doing here today with the TensorFlow user group in Bolivia. And I strongly encourage students to also join these events and to become more active with their own local TensorFlow user groups. If there isn't a TensorFlow user group in your local community or your city, and if you'd like to start one, please feel free to reach out to us, and we're very happy to help you establishing one of these user groups. The country with the highest number of machine learning GDEs is the United States, and that comes with no surprise. However, the number of machine learning experts is growing and growing in LATAM, and we are very pleased to see that. So our machine learning GDEs, as I mentioned, they are 167 right now. They are based in 44 different countries, and just last year they gave more than 900 talks and workshops about TensorFlow. The machine learning GDEs, they are critical in terms of expanding our outreach efforts. So if you would like to be a part of this brilliant group of experts, please do get in touch with us. Just to highlight some events where our machine learning GDEs speak at. These pictures are from the African Build-Up event and the Explore Machine Learning Day in Korea. This is Margaret, and she's one of our machine learning GDEs. And she says that she's the kind of person that when she sees a problem, she just wants to help. And this is the true nature and essence of what it means to be a machine learning expert. They are critical in terms of outreaching new developers and new local communities, but also they play a critical role in educating the worldwide community about TensorFlow. So how can you become a GDE? The process is very simple. You just have to be nominated by another GDE. You can submit your application. You will have one interview with one GDE and one Googler, and then you have the final decision. And you either join the program or you can try again later. But just to say that our GDEs, they are highly technical, and so it's not an easy process to become a GDE. So the last group that I would like to talk about is the special interest groups. Currently, we have 13 special interest groups and more than 2,000 contributors. They meet monthly, and they work in really close collaboration with the TensorFlow group. The special interest groups are a great way to create for bigger projects in which we have to work as a team. We created the machine learning special interest groups because they have a defined project focus, and this is a better way to organize contributors into focused streams of work. These groups take ownership of specific areas of TensorFlow, just like to add or maintain new features. Everything started with a SIG build in 2015, and now we have 13 SIGs, which is, again, very impressive considering the expansion that our community is seeing. Our contributor ecosystem includes the SIG add-ons, the SIG build, the SIG IO, networking, GVM, Micro, and Rust, which are all community-led open source projects, whereas the SIG Keras, Swift, and TensorBoard, they are Google-led with an open design philosophy. And as I mentioned, each SIG meets on a monthly basis, and if you'd like to be a part of a SIG, please feel free to join one on GitHub, where we will have all the information about the SIGs. But also, you can request a new SIG, and we're happy to guide you through the process if there's not one that reflects the contributions that you would like to do to TensorFlow. Just to give you a highlight of some of the existing SIGs, we have the SIG add-ons, which is a repository of contributions that conform to well-established API patterns, but implement new functionality not available in core TensorFlow. This SIG is a great way to stay up to date with current research and a really good opportunity for mentoring. They have a team of 9 maintainers that help review and mentor new contributors. The SIG build focus on building, testing, packaging, and distributing TensorFlow, and bridging the internal and external TensorFlow development. This initiative is led by Jason Zeman and Austin Anderson, and Jason is also a machine learning GDE. This initiative is supported by members from Google, Microsoft, Red Hat, IBM, and others. The SIG GVM, it's a comprehensive support for building, training, and serving TensorFlow models on top of Java Virtual Machine. This effort is led by Carl Lessard. And then lastly, just to give you an overview of another SIG that is led by community members, I would like to highlight the SIG networking, which is an extend a TensorFlow multi-node distribution with native support for HPC networking protocols and to lower the latency on networks, allowing scaling of networks with many small layers. And this initiative is led by Baron Wee and Jerome Bedorf. If you'd like to join one of the SIGs, we wrote a blog post that contains all the information on how to join the SIGs, but also what's the scope and more details about each one of them individually. So if you don't want to contribute with code to TensorFlow, there are many other ways that you can contribute to the community. And I like to differentiate them into three different pillars. One is user support that includes documentation, the creation of training courses, building use cases that support product development, community management through the organization of events and meetups, such as the one that we are experiencing today. And then lastly, project management. This is also a great way for developers who want to broaden up their skills and to try something new and get involved in the community. So now let's have a look at other programs that involve our TensorFlow community. So if you are interested in learning more about TensorFlow, you may want to consider doing one of our fantastic online courses on Coursera or Udacity. We are proud to announce that our university programs now include a TinyML certificate that we launched with Harvard, and we have many other programs available depending on your interest in TensorFlow. If you would like to showcase and acquire new technical skills, the TensorFlow certificate is a great way to do so. By doing the TensorFlow certificate, you'll increase your proficiency in machine learning. You can be recognized by the community, showcase your skills to potential future employers to say that you know how to use certain areas of TensorFlow. And if you're hiring for talent that knows how to use TensorFlow, then you can just head to our website and you can find all the TensorFlow certificate developers on our webpage. So far, we have certified more than 2,000 developers, and we have stipends available for those who require further support. I would like to give you a little bit more insight into the Community Spotlight program. This is a great way to showcase your work and your passion for machine learning and artificial intelligence. And it's a program in which we just want to feature your cool projects and demos using TensorFlow. So if you have one, please submit it to our Twitter form that is right there. And you can get your work recognized and featured on our social media networks. So far, we have recognized 18 winners, and it's a great way to reach out to more people in the community to inspire and get inspiration from. I would like to just share a couple of examples from some of our previous winners. One of my favorite projects is the one here at the bottom left, where you can see that your screen blurs when you don't have a correct posture. And I think it's just so useful now that most of us are at home and we don't stand up that much. So it's a great application of TensorFlow, really fun one for sure. For more information on how to submit your projects, there's the link to the form, and we look forward to see what you have created and to share it with the rest of the community. So if you are to remember a few aspects from this brief presentation about the community, is If you are an expert in machine learning, join the Machine Learning GDE program. It's a great way to engage with other experts from other universities or professionals in the area, and to really get the recognition that you deserve for your machine learning expertise. Do you want to contribute code to the parts of TensorFlow that you care the most? Join one of the special interest groups. Do you want to grow the community in LATAM? Start a TensorFlow user group in your region. Do you want to advance your career development? Then take the TensorFlow certificate. Are you an educator at a higher education institution? Please reach out to us to partner on the creation of a course. If you built a cool model using TensorFlow, please feel free to share it with the community and be featured on our community spotlight on Twitter. And if you have a cool use case or implementation of TensorFlow, be featured on our blog, submit your project and reach out to us. And don't forget to get social. Like, comment, share, and tag us on Twitter. We love to see what you are up to. These are our social media networks. So we have the Twitter account, our blog, and our YouTube channel that offers more educational opportunities on TensorFlow. So thank you so much. I don't want to extend myself as I know that we are at time, but if you have any questions, please feel free to reach out to me on Twitter, and I'm very happy to get in touch with you and let you know what program is the most appropriate for you to join. Thank you.
Thank you so much, Joanna. It's been a pleasure to have you here, as well to get to know a bit more about what's the different programs for GDEs, for TensorFlow community. I think it's super important to contribute to community and also to generate more content in Spanish, as we may have it in Latin America.
Yes, absolutely. I think it's so important that we have more documentation translated to Spanish, more blog posts, more content, so we can keep strengthening our community in Spanish-speaking countries.
Yeah, thank you so much again. And for sure, we'll give the information to your Twitter account and to the links for the TensorFlow community so people can reach you and also can show their different projects.
Fantastic. Thank you so much for the invitation, Leslie.
Thank you so much for joining us. Y pues ahora llegamos al final de este día de evento, que es el TensorFlow User Group en Bolivia, y hemos añadido a los eventos mundiales del TensorFlow Everywhere. Ustedes han podido ver diferentes charlas, diferentes presentadores, todos motivando al tema de contribuir a lo que es la comunidad y también de aprovechar todo ese conocimiento que hoy ha sido compartido para poder hacer sus diferentes proyectos. Los invitamos nuevamente a que puedan seguirnos en nuestro canal en YouTube, que es TensorFlow User Group Bolivia, y que también puedan contarnos un poco más sobre los proyectos que tienen. No se olviden seguirnos también en Meetup como TensorFlow User Group Bolivia, donde vamos a estar reactivando actividades para la comunidad y queremos saber sobre sus proyectos y sobre qué cosas también les gustaría aprender y pues trabajar en equipo. Así que manténganse conectados y será hasta otra oportunidad. Gracias.